Hello. In this lecture, I will be introducing the topic of procedural content generation. So, procedural content generation, or PCG for short, is simply the generation of content algorithmically. In our case, we're going to be most interested in video game content. And this can include all aspects of the media assets that you might need to create in your games. So certainly things like game levels, including terrain or rooms, hallways, buildings, but also artifacts, like the objects that the character interacts with. So these might be environmental features like trees and rocks, but also weapons, other sorts of objects, maybe even characters and creatures as well. This can include visuals. We can also use procedural content generation for sound and music as well. And we can even include elements that you might associate with the story. So the narrative, the quests and activities that the player might be tasked with performing. So all these different parts of the game we might apply procedural content generation towards. So you probably, if you play games at all recently, or even some older games, you're probably familiar with PCG and might be able to think of some examples that you either suspect of being generated or that you are aware of. So there are examples such as Spelunky. That's probably one of the most popular recent examples. That and, of course, Minecraft. There's also examples like Horizon Zero Dawn. In particular, they have a very elegant and sophisticated system for placing natural features in their environment. So trees and bushes and rocks. It's a very nice system. There is Dwarf Fortress, which generates an entire new universe every time you play it, kind of similar to Minecraft, but it actually goes further than that and generates a background history. In fact, it simulates out many steps of interactions between the different civilizations. There is Dead Cells, which is one of my favorites, that generates different dungeons with creatures to battle, and you can collect different weapons and abilities. And it, because of the way that it's always generating the environments, you never know for sure what you're going to be faced with. So it's kind of similar to Spelunky in that regard. There's also games like Sudoku and Nurikabe, which aren't really sophisticated in terms of any media assets that are needed, but instead there are the puzzle elements, and the puzzle elements are generated to a certain quality level that is appropriate for, say, well, first of all, the solvability and also difficulty. So there's certainly some interesting aspects of procedural content generation when it comes to constraint-based puzzles and being able to work within those constraints to come up with appropriate content, such as the unsolved boards for either a Sudoku or a Nurikabe puzzle. Now, with the good comes the bad. There are also bad examples of procedural content generation. There is No Man's Sky, which sort of became the go-to example for where PCG did not work out. Though I can say that this game has continued to evolve with patches and refinements, and it is perhaps a much better product than when it first came out. But in No Man's Sky, while there was this potential for randomness and therefore lots of unique, say, planets and creatures, there were criticisms to early versions of the game that it was all very monotonous and just slightly different skinning, that the quality of the generation was not very good, such as like if you look at the creatures in this screenshot, they don't look nearly as as compelling as the showcase examples pre-release of the game. So I think it might have been a video for E3 or a similar sort of trade show when No Man's Sky was first introduced, and it looked like these amazing dinosaur-inspired creatures. And while those sorts of creatures are certainly a possibility, just the broad range of like limb and body types that can be combined can end up with some that are not very aesthetically pleasing. And again, the game just overall, even though there is this broad variety in terms of the gameplay in those early versions, it just wasn't compelling after some short period of playing the game. Mass Effect Andromeda kind of had a different situation. They were relying heavily on this tool World Builder that was going to help to generate the different planets or worlds that you could go to. And so they had some very specific ideas about the game design, and those that design philosophy or the desire for their vision, it did not mesh well with the capabilities of World Builder. Ultimately, after having made promises about what the game was going to deliver, they had to abandon use of World Builder, or at least limit their use of World Builder. So they were not able to create the intended product using this particular procedural content generation tool. All right. Yeah, and here is, if you're interested, a link to the a background story if you're interested in more about the problems that the developers face with Mass Effect Andromeda. You can check out that link. You can also find procedural content generation used in somewhat isolated situations in games. There are certain, you might think of it as like low-hanging fruit. There are parts of games, especially as game designers have sort of transitioned to using PCG more and more. They're picking select areas to apply the principles of dynamically generating the content. So there's things like Speed Tree, which is a tool for creating unique trees with random elements, but still following sort of a natural order and aesthetic. And there's similar tools that you find for other types of objects. There's also the example in Borderlands, that series, with the generation of different weapons. And again, this is a very sort of self-contained sort of application of procedural content generation. So varying the number and size of barrels on the weapons, whether they're handheld or not, using different sorts of constraints on how the geometry is defined on these different guns, and also different decals and other aesthetic sort of aspects. And so that is seen as a big success. And it's interesting to consider the Borderlands example because it's not just randomly generating different looking weapons. It's actually coupled with some utility, some value to the player. And so if we think a bit about that, actually drawing from some of the discussion that comes up in my video game design class, we can consider the impact that the randomly generated weapons have related to player reward. So the weapons can be obtained by performing in-game tasks like beating an enemy and then collecting the loot. So we can consider how often different rewards are obtained. So you might have some rarity to the generated weapon, some aspects of the procedural content generation such that you rarely have certain valuable attributes that are presented. So you might occasionally have weapons generated that have extremely high value, and therefore they're valuable to the player, but that you don't see them very often. So they are rarely occurring, or rarely being found. And then there's maybe more common weapons. And so the procedural content generation to be coupled with a sort of reward schedule can be appealing. And you can also couple this with operant conditioning. And this is looking more closely at the overall reward schedule. So the player encountering multiple battles and multiple opportunities to collect loot and these new weapons that can be presented with a random ratio schedule. And this comes from early operant conditioning research of the Skinner box, the study done with rats. And so this compared different ways in which a rat could be rewarded for pressing a lever. So there's like the fixed interval schedule where the lever had no impact. It just the food came out on a time-based schedule of a fixed time length between distribution of the food. There was a fixed ratio schedule, which is food comes out every n times the rat presses the lever. So you could have like 1-to-1. You press the lever, you get a food pellet. And you might think that the rat would maybe change behavior if it was a different number of presses. So say 2 presses or 3 presses, that gets a food pellet. But they quickly learn that as well. And just whenever they're hungry, they will get the food. But the random ratio schedule, that has addictive properties because the rat has trouble learning how many presses it takes to get food, because sometimes it'll be a very long number of presses before the food comes out. Sometimes they might get what you would call like a hot streak, getting lots of food. So that works on humans as well in terms of reward. So you can see how procedural content generation can fit in nicely with some of these game design concepts, understanding that humans have these addictive like tendencies in terms of gameplay and therefore what they find appealing. So coupling the procedural content generation to introduce this rarity and utility to the player can show where this is an example of procedural content generation that was very effective. So it's a bit different than, say, having 100,000 different creatures through a huge universe, but where everything's really kind of the same. That this is maybe a little more a better use of procedural content generation, at least from the eyes of the game player. Now, there's some early examples of. Let's see. I think let me go to this Next slide. Sorry, I got a little mess up here. So early examples of procedural content generation. So it's actually been around for a while. So as at least as early as 1978, we had Beneath Apple Manor, which is considered a roguelike, though it actually predates the game Rogue. So it's generating these maze-like structures and has object placement, and I believe it has permadeath as well, which is a feature that you often will see with some of these procedural content generation games, so like the dungeon crawlers. And of course, the game Rogue in 80, and then Elite, which is a space flight game with generating a universe. So somewhat like No Man's Sky. So all of these games use procedural content generation, either for generating these dungeons and objects that are placed around, or in the case of Elite, generating this universe with planets with different attributes and so on. So it certainly is not a new thing. That while there has been this gain in popularity. All right. We also see procedural content generation used in a supplementary sort of way. So this is related to maybe picking out certain aspects of the game, such as individual media assets or artifacts, a part of the gameplay. But maybe instead of an artifact, we can look for some part of the gameplay. And so we can add depth to the game. You see this fairly commonly in RPG type games. So this might be to broaden the opportunities to play the game, maybe extend the length of the game. So for instance, we could have side quests in a game that the player can participate in, strengthen their character, build character stats through playing through, but that is not part of the main quest that or the quests that are tied to the story. One early example that I can think of and played some was the Elder Scrolls Arena game. So this came out in 1994, and it actually had a lot of side quests that were randomly generated. You could talk to randomly generated characters who would give you tasks that were very mundane, as I recall. So a lot of like delivery or being sent to a dungeon, and you would have like some particular character to kill or an object to find hidden in the dungeon, and all of these were randomly placed items. And Elder Scrolls has continued to rely on procedural content generation for the side quests in their future offerings. Even in Skyrim, they had their Radiant Quests system, which was similar to the original Elder Scrolls Arena, except with some improvements in terms of the quality of the puzzles and the scenarios generated. So it's pretty primitive in Elder Scrolls Arena, but did improve over time. There's also the example of Bloodborne has their Chalice dungeons. So some of the dungeons had a randomized element to them, though they would all follow a general pattern of, I believe, certain rooms and structures in terms of entering and then recognizing, like when you were about to where the boss was, and of course had the boss battle. So these features for each of these games added to what was possible and what you could do in the game. There's also the game Dwarf Fortress, which is well regarded for its use of procedural content generation. So there is a section in a book, Game AI Pro 2, by Steve Rabin. So he's got a little section where Dwarf Fortress is discussed, and also you can find some talks like Game Developer and similar talks about what went into the development of Dwarf Fortress. But Steve Rabin just says that Dwarf Fortress procedurally generates the entire world from scratch. The process begins with an elevation map generated based on randomized fractals. Next, it creates several map layers, which include temperature, rainfall, drainage, vegetation, and salinity. With the raw components of the map defined, the next step classifies each tract of land into different biomes, plant and climate types, such as woodlands or savannas. In the next phase of the simulation, temporary rivers wear down the mountains, followed by permanent rivers that flow from high ground to low ground. Plant and animal populations are then introduced, followed by world-specific fantasy creatures. At this point, the world creation is complete and the simulation of civilization begins. Through this process, settlements are raised, trade routes are formed, and wars are waged. At a designated point in time, the simulation stops and the player begins the game in a unique living world. So there's an entire world, not just the terrain and geographic features that are generated, but an entire history is generated, and then the player joins in. So it's not like this static world that's just sitting there waiting for the player to begin participating. It actually went through an evolution that included long-term simulation of the effects of like water erosion. In fact, these are common approaches. Modeling those sorts of approaches are common in procedurally generated terrain. All right, so some reasons why a game developer might choose to use procedural content generation. Well, there's some I think obvious benefits. One that's probably pretty important in many cases is development cost savings, especially if you take into account the cost of generating high quality modern day video game assets like 3D models and textures. There's a significant cost of developing a game goes into developing those sort of media assets. So if you can generate them with procedural content generation algorithms, then potentially you can save a lot of time and money. But there's also storage costs. So especially those early examples of the use of procedural content generation was often driven by the very limited storage on early PC computers. So if you could just generate something on demand as needed, that meant it didn't need to be stored on a floppy or a cassette or whatever sort of storage was available on those early PCs. And the same is true today. There can be situations where you might otherwise need a huge amount of storage to define where all of these objects are. Horizon Zero Dawn comes to mind with its placement of objects that is driven by a small number of control textures that define probability maps, the likelihood of objects existing in different places. And there's a kind of an elaborate layering approach to driving that. There's also replayability benefits from procedural content generation. So if you can generate new and unique, compelling content, then the player will stay engaged with your product for longer than if you otherwise had a smaller amount of handmade assets. There's also the potential for customization, tailoring an environment maybe to user preference, and perhaps even doing so dynamically, including adjusting the difficulty of the game. So whether it's like being able to jump from platform to platform, or the challenge of the enemies, or the strategic aspects of the game, if you can figure out how to measure what the player is thinking or feeling, or the difficulties they're facing, you might be able to parameterize your procedural content generation and then be able to adjust so that the gameplay experience is most appropriate for what the player is experiencing. So just to go into a little bit more detail about why use procedural content generation. So of course the cost of the content. So there can be like the low-hanging fruit sort of opportunities where what are clever areas of your game that you might be able to apply procedural content generation without having to fully embrace procedural content, perhaps. So this might mean using speed tree to generate the trees in your environment, or maybe generating certain types of objects. But you can also run into complications if you rely on it too much. It might you might have a mismatch between the capabilities of your generation of content and the design goals of the game. So you can refer to the Mass Effect and Andromeda game and the problems they had with World Builder. It can also address as games move towards more and more realism, the exponential increase in cost. So the cost of making new content. So to make like levels or maps in modern games compared to, say, games 20 years ago, we're probably looking at like a couple orders of magnitude difference in that effort. It's also the content that is made that can, if developed effectively, like the Borderlands 2 guns, then this can really be interesting and exciting for the player as compared to not using procedural content generation effectively, such that it doesn't have the appeal. It's not associated with reward or utility in your game. The having this generated content, so we've got the development cost savings, but also this potential for storage and memory utilization. And again, this getting the player to play and replay the game over and over, adapting to the player. So there is a great example in Left 4 Dead. They have an AI director. There are internal metrics that try to track what the user is feeling or experiencing in terms of difficulty that they're facing, frustrations, and then being able to adapt the content procedurally to work effectively with the player, based on how they performed previously. So the player is able to participate as part of this feedback loop and the content that's generated is responding to these parameter changes. We also see, like in a game such as Spelunky, we avoid the player being able to have success in the game by simply memorizing the level. So the early examples of platforming games like Super Mario Brothers could be quite challenging, but you could get better at the game by simply memorizing the levels. You knew exactly where the Goombas were, and the collectibles, the coins, and the mushroom power-ups, and so on. But in Spelunky, you have to instead craft your skill or develop your skill at playing the game, understanding the mechanics, the universe, and never being able to completely memorize the game. So it's a very different sort of gameplay experience in terms of replay of Spelunky versus replay of Super Mario Brothers or many other platforming games. So definitely some benefits to using PCG, and can pay off and add value to game development projects. There's two main applications of procedural content generation, two different approaches that you can take. So one is that you can have runtime procedural content generation, and this is where you generate content live in the game. So there is No Man's Sky, Spelunky, Minecraft, Horizon Zero Dawn. There's lots of examples where content is generated at runtime. But then there's also the approach of design time use of procedural content generation. So this is using PCG to generate and then pick the items that you like, or the iterations that you find valuable, and you save the content. So you don't get like the storage benefits, but you do get this rapid generation of content. So the designer is able to vet what is generated. You might even generate some baseline and then edit it. So Skyrim used this. The artists, level designers in Skyrim generated parts of the world, and then things they didn't like they could refine and change. Horizon Zero Dawn, actually, we can think of as more of a hybrid between real time and design time, because the artists were able to interactively change these density maps for the object placement. So in some cases, they would say just take automatically, based on rules defined, these different creations of like rock placements or tree placements. But then if they didn't like something, they could go into one of the probability maps and then just paint onto it. So they could actually do this within a special editing, like live version of the game, and then just change the placement of objects. So it's kind of had the best of both worlds, both the runtime and the design time. So the artists were able to override the generation, but still kind of seamlessly transition between what the artist controls completely and what's controlled just by constraints in their rules engine for combining the different types of noise sources and other features. So design time versus runtime. Of course, with design time, we're mainly speeding up the design of the static content and reducing the cost to obtain the content. Whereas runtime, we get these additional benefits of, say, being able to customize, dynamic adjustment, also the storage benefits that we get from runtime. But there's trade-offs, like you don't get to vet or approve of what's generated. You can do some trial runs, but you never know necessarily what's going to be generated, especially if your world is not constrained. Like if the player can just keep moving on forever or keep causing new things to be generated, then you might generate something that doesn't work in terms of gameplay or is inappropriate in some way. With design time, procedural content, we have graphical asset construction that consumes a lot of development time if it's done by hand. And again, games are increasing in complexity and the number of unique objects. And furthermore, there is more and more demand from players. They want high quality games. They don't want to see repetitive aspects of gameplay or the content. And some of these blockbuster games that we see nowadays can have hundreds of man years with huge design teams. So there's a lot at stake when you're making these big, expensive games. So anything you can do to reduce costs, there's value. So this is a strong motivation for use of procedural content generation. But the risk are you maybe get unexpected results. Even if you are able to review or vet the results, you might not have any choice in terms of what you use, depending on the capabilities of your algorithm. It might result in content generated that's at odds with your intended design. So these are the sorts of challenges you might face, especially as big, complicated games rely more and more on procedural content generation and maybe either don't fully understand the tools or are developing the tools as they go, and don't know what their developers that are assisting the content designers, they don't know what the end result is, what the algorithms are going to be capable of. So design time, procedural content generation will generally involve using some sort of tools, and the results are vetted for inclusion in games. So some examples we've already seen discussed SpeedTree. There's also Esri's City Engine that can generate procedurally generated cityscapes, so like streets and blocks and buildings and so on. There is Terragen, which can be used for generating terrain. It originally was popular for creating terrain for movies and commercials, that sort of thing. But they also the tool can be used for making video games as well. And they've gone through some iterations of their tool. So we can consider the payoff that we get from using procedural content generation versus handcrafted in this sort of idealized graph here. So you can think of this trade-off in terms of the amount of gameplay that we're attempting to develop. So what amount of content do we need to develop versus the total cost? And so the use of procedural content generation has a lot of upfront costs, either developing the tool outright or learning how to use the tool, understanding how to constrain what is generated. And so those upfront costs might not pay off necessarily if you're only developing a small amount of gameplay. But after a while, the curve begins to flatten out in terms of the cost, because you've sorted out all of the issues. And to make more and more content is just no more difficult than just running the tool more, not having to, there's very little human effort that goes in, maybe some vetting or screening depending on what we're talking about. whether it's offline, like developer assisted, or if it's runtime generated. But handcrafted assets will always have this same slope, this same cost. Anytime you want to add more gameplay, you got to spend that much more time developing and hire that many people to develop. It's important to consider how you're applying procedural content generation related to the types of content. You might have single-use items. You might have reusable items. So you can think in terms of like, well, the player character, that is a very important game object. A lot of subtlety and movement and control. That's probably the sort of thing that might best benefit from being handcrafted and really refined and iterated on and polished. But then there's single-use items like, say, a chair in a house. These are things that aren't necessarily very important, and those are the situations where you might benefit from, say, procedural content generation. It's a single-use item in the sense that you only need to say make one unique thing for one particular setting or venue in your game, and so you don't want someone spending a lot of time making that like an artist. Instead, those sorts of objects are good candidates for procedural content generation. Even if the procedural content generation is not as good a quality, it can still it'll be passable. It's not necessarily items that are going to be front and center, the focus of the game player. Even if they are scrutinized, the player's probably not going to spend a lot of time with it. It's more about the overall setting that you are generating. So if lots of objects, lots of features in the environment, maybe if occasionally things are a little bit off, the player's probably going to be pretty forgiving. So understanding the types of content and where to apply the procedural content can be beneficial. In relation to runtime procedural content generation, we have this opportunity. So we know that all players are different. They have different preferences and abilities. And so as soon as we know that we have runtime generated procedural content generation that's probably parameterized, well, we can play with those parameters by including the player in this feedback loop. So I mentioned this some previously, but we might be able to change the difficulty or the challenges. We might be able to figure out the player's taste. We might be able to figure out players' exploits and make adjustments. And so that can be very interesting. This is almost more of like a research area, or certainly a more recent feature of some video games. So if you want to be able to make these sort of adaptations, of course, this suggests that you do want real-time procedural content generation. That you might also be motivated by storage limits, as mentioned before. And so we have this. If we're talking about generating procedural content generation at runtime and adjusting to the player, then there's this optimization problem that is introduced, and this is where the challenge comes in. And so that is how do we determine the set of content or the parameters of the content that's going to give the optimal experience, either in terms of preference or difficulty and so on. So there's some risks associated with using procedural content generation. And these can be certainly a lot worse with runtime generation. And that is the generation of content procedurally can be an NP hard problem. You can end up in situations where you're not your algorithm's not going to work well for runtime generation. Also, testing is certainly a challenge. You can't test every possible scenario, just all the different permutations of the parameters. You can really have a lot of trouble there. Any sort of PCG has the potential to generate offensive material as well. So, if we were generating names or words, just random combinations of characters might make an offensive word. That's just a very simple example. You could have other structures or visual imagery that could end up accidentally inappropriate. And even if this is offline or designer assisted sort of development, you have to really scrutinize everything. If you're just kind of giving a quick overview to content that you're pre-computing, you might still miss things. And even if it's not offensive material, you can still have bad content or impossible gameplay challenges. Maybe the player can't jump from one area to the next or traverse between areas. You can also have issues with algorithms that crash, in terms of guaranteeing computational stability. There's all these challenges introduced by procedural content generation. You can also end up with meaningless activities, it might be easy to create quests, such as we saw in Elder Scrolls Arena, but they're very mundane. They're sort of disconnected and isolated, and no one really cares about them other than just grinding to generate, get experience points, and that can become a boring part of gameplay. So challenges with procedural content generation: story elements, any sort of interactive narrative is still a big challenge and an open research problem. There's algorithm stability that we talked about before. So infinite loops, unanticipated jumps in complexity, like you trigger certain paths through the combinations of interacting elements in your algorithm, and then suddenly it's running a lot slower. It's really hard to avoid in certain circumstances. Also open problem is automated auditing and vetting, so you don't have to have a human that goes over the content to confirm, inappropriate content or that it's appropriate in terms of the gameplay, like being able to jump or traverse. That can be difficult. And then for using runtime PCG adaptively to fit the human player as appropriate, this requires modeling human players, understanding what their needs are, what their wants are. That's an open problem, not yet figured out. Probably never will be completely until we can read people's minds. Understanding what human players find interesting and when they notice repetition, that's another big one. So you want to be able to randomize the interesting aspects of the game and keep it interesting, not mundane. So lastly, we'll wrap up with objectives of PCG. So probably first of all, we want to have PCG that to capture design and asset creation expertise, but we want it to encapsulate that in an algorithm. And we want the result of applying that algorithm to result in reliable and consistent quality of the content generated. And lastly, we want to support gameplay that would otherwise be impossible without PCG. So we're opening up new genres and styles of gameplay with PCG. And that's probably really the most exciting thing about the recent popularity of procedural content generation in games. Hello. In this lecture, we're going to look at random number generation and its importance for procedural content generation. So when we're generating our procedural content, we need some sort of information source that's going to help us to define parameters in models or algorithms that actually do the work of generating content. There's usually a very large space that is defined by an algorithm. There's not like one path to generate what we want. There are configurable parameters, and these parameters could have like continuous ranges or maybe integer values, but there is a configuration that we might set initially, or we might have to constantly provide new control values. For instance, if we have a Bezier curve that we're using to define a road or some other type of path, we might have some initial segment, the one piece of a curve, and so we would need some configuration of that. And so there's near infinite number of possibilities there, setting the anchor points and the tangent control points for one segment. And then if we want to continue the path, we'd add another segment, which would have an additional control point, and depending on how you're controlling the tangents, you might be adding two new control points that may or may not be constrained in some way, depending on if you're keeping parallel tangents across control points. But the important thing here is that there's this configurability to this particular model. So in this case, our curves, but we might have some other type of procedural content like terrain, or textures, or other types of content we might want to generate, maybe music or sound effects. And all of these will generally have a lot of possibilities for parameters. So the random number generation, if we can generate values, then we can plug them into these models, and that will provide us then with the output content that we desire. Now there's some challenges here. One is that in many computer science applications, especially in recent years, with the importance of cryptography and making sure that the internet applications are secure and cannot be exploited, there are a lot of random number generators that strive to have something approaching true random values. So while there might be an algorithm involved, you might find, say, processors that have some kind of hardware support that at least partially provide some values that are maybe based on the laws of physics, and being able to extract certain characteristics from measurements, say, of like the way things, the way heat spreads between different materials, maybe monitoring background radiation, possibly you have measurements from the user, like their mouse movements or other types of interactions with the device. And so from those sources, there might be some information that's then passed on to a random number generator algorithm. And so that natural random information is sort of mixed in with an algorithm. And so that's very useful when you are concerned about things like security and making sure that hackers can't break into your computer. But this is not necessarily something that is desirable in terms of an information source for procedural content generation. Generally, when you're talking about procedural content, you want to be able to recreate that content anytime you need it. And so we would like to have the ability to create a random sequence and then be able to recreate that again later and not have to store the entire sequence like on your hard drive. Instead, we'd like to just be able to store the starting value, and from that starting value, generate everything needed to, say, control our Bezier curves or our terrain generation or whatever other content we might want. So if we do not have this ability to restart our random number generator and get the same sequence, then we would not be able to recreate the content. So many of the procedural content generation applications that we've talked about before, especially, say, the being able to minimize storage requirements, we would lose out on that to a large degree if we did not have the possibility of random number generation that can be defined just from a starting value and then work from that. Now, in terms of what you get from the random number generator, generally what you want is a uniform distribution. So by that I mean that all values are equally likely to occur. And we will generally see two flavors of the random number generator. So you may have continuous floating point values, and this is often within a range, say, typically this is from 0 to 1. And of course, you can just multiply this by your desired range, and you can calculate any range you want, starting from that 0 to 1 normalized scale. Some APIs will let you pick other begin and end values and do all the work for you. And there's also discrete versions. Many APIs provide both, so you can generate integer values within a range, and so you specify the start and the end, and they vary depend on if it's inclusive or exclusive values in the range. But once you tell the random number generator what you want, the value you get back is uniformly distributed within that range. So any possible value within that range is equally likely to occur. So this is a good starting point, even if you do need other distributions of data. They're generally pretty easy to calculate by starting with a uniform distribution and then plugging that into an equation, and then so you can get like a Gaussian distribution or maybe a Poisson. Though the computational costs will vary depending on what the nature of the particular distribution that you're generating is. So back to the topic of this repeatability of our random number generating algorithm, or a pseudo-random number generator. So we call it pseudo-random because it's not actually random. It just has the appearance of being random. If you, say, analyze the values that are returned in a sequence, so you can analyze them and you can see that they're uniformly distributed and that the different there's no detectable patterns in the values, so that they have nice properties in terms of how these random values are spread out. So if our particular algorithm can use a seed, meaning a starting configuration value, this is called a mixing function. And the reason it's called a mixing function is that the bits of the seed they all have an influence in the bits of the generated pseudo-random number. So that means if you say had two seeds and they were only different by like a single bit in the same position, then the same algorithm, same pseudo-random algorithm would generate very different values that are potentially different in all the bit positions of the output value. So if you seed the same algorithm with the same seed value, then you get the same result. And if you keep calling the algorithm with the updated value, or so the updated seed or internal state, if that's excuse me, if that's maintained, then you get back the same sequence of values. So our mixing function is defined by this process where we start with a seed, and when we ask the pseudo-random number generator to update, a new seed is generated along with the value that's requested. And so this value would be used in the application. The seed would be maintained perhaps internally to the random number generator API, or it might be the responsibility of the developer to track this seed somehow, maybe in, say, an object, and preserve a reference to that object, and then call it any time that another value is needed, and then that seed will be updated as necessary. So again, the fact that we have this seed value with the mixing function means that we can recreate the sequence of random values that we need. So we might store this in our game data. We can initialize our algorithm with the seed, and then we can make requests to generate as needed one value after another, and we're going to be guaranteed to get that same sequence. But there's a challenge to this. So while we will be able to get this same sequence of values, we have to be very careful when we're developing procedural content generation solutions, that we are always making the exact same number of calls to the random number generator, that we're always putting the values into the right place in the procedural content generation algorithms, so the correct coefficients or parameters. And we have to watch out for contention. There are often multiple systems or subsystems within a game that all contribute to procedural content generation. So you might have algorithms that deal with generating terrain. You might have algorithms that deal with, say, generating the clouds or other features of the game. And so as the game evolves, as the game is developed, you can have the some change in the content, change the order in which the random number generator is called. And so that is something that you have to be very careful about, is that you might, say, work with a particular concept level, like you get some initial procedural content generated. The mountains are just where you want them. The canyons and other features are exactly perfect for what you want. And you start to build up other procedural content around that. And then if you're not careful, you end up losing the creation that you had before. and so that can be certainly frustrating. Now you also need to watch out not just for the evolving code base causing changes, but you can have non-deterministic effects as well. So, for instance, if you're not careful, you can end up with a frame rate dependency. And of course, if the frame rate varies, then that might change the nature of the way that the random number generator is getting called, making these requests to generate content. And so you can just end up with a completely different experience every time the game is played if you end up with a frame rate dependency. You can also accidentally have dependencies on external events that likely would be triggered by actions of the human player. So as the player is deciding to move around in different ways, they might trigger content to say be generated incrementally, and you have to be very careful in those sorts of scenarios. You might trigger the content in a branching nature where you can get different outcomes different ways. And if your intent is to always like create the same level every time, then you might break that and end up with different results every time the player or other different players play the game. Here is a brief look at what Unity provides in terms of their random number generator. So their solution is interesting because they don't have a persistent ability. They have a one-way direction to get the seed into the game, but they actually maintain state with more data than a single seed. So they have like a you can initialize the random number generator with a init state and pass in an integer initial seed, and but once the random number generator is initialized, internally it uses a number of different values beyond just 32 bits. So there's more bits than 32 to maintain state. So you cannot get a seed back out, for instance. So you can initialize with a seed, but the only thing you can get out is what they call state. And so the state is that collection of more than 32 bits, and it's not accessible, but it is serializable. So that means that you can preserve the state and perhaps save it like to a save game and then get it back, and then including reinitialize with that state. And so that's done. You can set the static member variable, class variable, random.state, you can set to a preserved or serialized state. And then, of course, you can query for new random values, which update the state every time it's called. So typically that's going to be random.range, and you can use integers or floats. So the fact that you can initialize with a seed and also be able to save and read the state makes this a good solution for procedural content generation. And furthermore, you can run into an issue where you want to isolate your random number generation between your different subsystems. So the Unity solution happens to work well for that because you can maintain these separate state values. As you switch between subsystems, every time there's a context switch, you can just set the state to a preserved value. So each subsystem maintains its own state value. So when the context switches to a particular subsystem, it would set the random.state class variable and to its state. It would make its calls to random range or any of the other output methods that can be called. And then when it's done and ready to context switch out, then it can save its state. So it can always come back to right where it was before. And so this works well, and the other APIs work similarly in other game engines and general purpose programming libraries that you might find will often have something similar to what we just looked at. The general approach is you kind of have a tree structure to this. So you might have a root level game manager that is seeded with a particular value, and then each subsystem refers to the game manager to get their own initial state. And so everything sort of branches out from that root, and you might have subsystems of subsystems with like particularly complicated solutions, and so each one just needs to store their state value, make sure that they load it when it's their turn to generate, and then save before their turn is over. Now, if you are using a random number generator provided to you, you need to be cautious because there's potential for there to be differences between, say, platforms. So you might have, say, different implementations in, I know JavaScript is one where you don't know what you're getting necessarily. To meet the JavaScript standard, there I think are at least a couple different valid solutions. So that would mean you would have platform differences if you're trying to generate, let's say, a procedurally generated level in like a web game. So you probably would be better off considering just using your own implementation where you have full control of the code and can maintain the portability yourself if you're deploying to multiple platforms. And so that is actually a recommendation in the Millington Game AI book, and so he often will in the games he works on will use his own portable code with an implementation that he can fully trust. Last thing I want to mention about random number generation is the quality of random number generator. So I started off by telling you that the random number generator is a source of information that we're going to plug into a parameter space of algorithms or models that we have for, say, generating terrain or paths or the various possible things we might want to create. It's important to realize that random number generation is often too noisy to use directly. It like here we see what would happen. This is from Millington's book, where he shows what would happen if you just directly use a random number generator for each height map level in a height map for terrain. So if you just walk through the X and Y positions with like a nested for loop, and then for each pixel, keep calling the random number generator. You can certainly do that. And what you'll get will look like carpet in terms of heights, or if you just looked at a raster image, it looks like static. And doesn't make for very compelling content. It's got way too much high frequency noise. We would prefer to have lower frequency that's more in line with natural features. And this is a common sort of problem that you run into with a path. If you try to generate, say, a random X and Z position to define like a 2D path, it's going to just be jumping all over the place. Even if you constrain the ranges so that the length, each segment length is only so long, you're just going to have what looks like spaghetti if you don't further constrain it. And so using something like cubic Bezier curves it provides a nice constraint and allows you to have smooth, natural looking like roads, for instance. So it's really important that you're identifying an appropriate model or algorithm that you're going to be plugging your random number generation into. and then that's really the key to getting quality content for procedural content generation. Hello. In this lecture, we're going to look at terrain generation as an application of procedural content generation. So with terrain generation, we can work with what we know of real-world terrain in terms of the dynamic natural processes that have formed the terrain that we're familiar with, and that we have some understanding of through various scientific fields that have studied, say, geology and the changes to terrain over time related to tectonic plate movements, volcanoes, the way that rock and soil can be manipulated through these processes, and how the different physical properties lead to different types of structures. And so this can be with emergent physics-based simulation, or through some model that has been fitted to observed data. Similarly, we can look at the effects of climate, which includes wind, like the erosion and movement of materials like soil. Same with water, how it can carve through terrain surfaces, glacier erosion. There's also temperature-driven changes. So there's lots of knowledge and models that can be leveraged in terms of terrain generation. That said, these the potential algorithms that we might use could get rather complicated and maybe beyond what we want to use in terms of video game terrain generation. So we probably don't want to build a world completely from scratch and based entirely on physically simulated processes. Instead, what we might do is start with some more abstract process that roughly models features that are maybe similar to what we see in the real world. And then once we get to that baseline, we could then have some simplified approaches to applying weathering type processes. So that would sort of give us the improvement in efficiency. We can more quickly get to a starting point rather than building from scratch. And then we can add to the surface of what's created many fewer steps of any sort of like weathering simulation, but still have it look like a world that was fully the result of those sort of natural processes that we're familiar with. So to get that base terrain that we're going to start with, we need some way to define these basic shapes. So a good place to start would be a random noise source, like a random number generator. The problem, though, is that your typical random number generator with uniform distribution, you're going to have too many frequencies, especially high frequencies, and they're all of the frequencies are going to be at the same magnitude. So you're just going to see static or just lots of spikes, and not any of the sort of natural fractal sort of structure that you're familiar with in like natural settings. So it would really be nice if we had some other way to define our noise. And so a popular approach is Perlin noise. So we can see here uniform random noise that just is like white noise, static. And then we have Perlin noise on the right. And so Perlin noise is, you can see there is higher frequency noise present if you look closely, but it's much more, the magnitude difference is much smaller relative to these lower frequency features. So you can see like kind of rolling hills or puffs of smoke from this perspective in this image, and there's texture to them. Those are those higher frequency details, but they're not so extreme as you see with the white noise. So this looks much more natural. You can probably think of real world things you've seen that look similar to this. And so if we can make noise in this fashion, that is going to be a way we can get much more realistic looking features. So actually, with the Perlin noise, it's typically layered to get the different frequency ranges. So by itself, you have a gradient noise that's based on a lattice, and you at minimum will have a 2D lattice, but you can go to higher dimensions as well. So it's pretty common to go to 3 dimensions, for instance, and so that would work well with voxels. For terrain that's height based, that 2D is fine for that. So just at a high level, the way Perlin noise is defined is, again, you have a uniform grid, and then there are at each point in the grid structure there is a seeded random orientation and a magnitude within some range, and so this controls this controls a weighting effect that is used to determine intensity at the sample positions that are in between these control points. And so a neighborhood in any given pixel is found relative to these neighboring control points that are aligned to this lattice, and a weighted determination of that given pixel's value is found. And so the end result is that there is a gradient calculated because of the interpolation between the different control points. So like if a pixel is really close to one control point, then it'll be primarily influenced by that one. And since these are all randomly assigned, you get this nice gradient. And so the way that Perlin noise is typically used is you don't just use the gradient one time. You actually layer it, and it can be offset. The different layers can be offset, and it's also generally used in a tiled fashion. So you can determine the the control points in the lattice can be set in such a way that if you align like top edge to bottom edge of a copy of itself, that it fits perfectly together so that the interpolated gradient smoothly transitions as it wraps around top to bottom, left to right, right to left, and so on. So this makes it really easy to work with, and it works especially well if you have a situation where you want to tile. So maybe tiling a terrain, or if you can use Perlin for generating textures as well for texture mapping, and it can work well for that situation too. So once you have your ability to calculate the Perlin noise, you can again you can layer it so that you have different frequency ranges that contribute to, say, the height map. So you have some lower frequencies, which would be it would appear as like large features such as mountains or hills, and then you could have a lower or rather a higher resolution layered on top, but with a limited magnitude. So you wouldn't have the next layer applied on top to have the same magnitude as the layer that was lower frequency. So when you do that, what you end up with is it looks like you have, say, large mountains or hills with smaller features that are sort of layered over top. And this is normally done as octaves, so they're multiples of one another. And it can give very compelling features. And there's nothing that forces you to go strictly with octaves. In fact, in the starter project that's used for the procedural content generation homework in the class, there's no restriction in how you set up each of your layers. So you can pick like an arbitrary scale for multiple layers, just as you please, and you can play around with different offsets for each of the layers. And then so that gives some freedom to just refine and try to get the desired combination. But with Perlin noise, it does have a predefined and limited range, and therefore it's going to repeat. But even with a repeating, it's often difficult for someone to notice because of the way that the multiple layers can interact, and then you can have other types of terrain generation features as well. And so it can be a while before any obvious repeating is noticed. But you might notice that there's common sorts of features that are repeated, though not necessarily exactly the same. And so the fact that it can tile seamlessly is especially useful. So once we have this ability to layer Perlin noise, we might think about ways to have more flexibility and more control over this process, and we might even introduce additional capabilities. And so you can make some pretty elaborate terrain generation rules just by working with Perlin noise. And so we have the homework project in the class working with procedural content generation, and it works by creating it supports the ability for the user to create a tree structure, and you could even have a directed acyclic graph with branches that merge back if if we had a graph editor that supported it. So the current project is just using the scene view in Unity rather than a full-blown graph editor. But it could, there's no reason why it couldn't be with a directed acyclic graph, which would open up a few additional possibilities. It might even be possible to leverage Unity's shader graph structure, and that's one thing that I'm interested in looking at implementing, is seeing if I can move the tool to use that, and you would additionally gain the benefit of running the terrain generation largely on the GPU, so that you could get some performance improvements from doing so. So, but the general idea is that you can create this graph structure. Each of the nodes have responsibilities that allow the user to declaratively define rules for terrain generation. So one important aspect of the nodes of the graph is to generate noise through some sort of constraints, such as the scale level or the zoom level of the Perlin noise, as well as offsets. There may also be remapping functions that take the generated heights from the Perlin noise and just run them through some function that remaps them. You could even use more elaborate sorts of mapping, such as a convolution. So in the case of your typical terrain, you have a 2D height map. And so not only can you remap a pixel based on its previous value, but you could also remap a pixel based on its neighbors. And so a convolution is a process where you can look at the neighborhood of a single height value and then change it based on the heights of other height map pixels around it. And so you could get some interesting effects by doing that. I've played around a little bit with doing that, but I haven't fully integrated that in. But this is something that could easily be applied if you were running in like Unity's shader graph or made your own GPU-based implementation. The convolutions could be pretty efficient and would open up some other possibilities for terrain generation. So that's just generating the noise. But there's also probably the most powerful capability with this approach is by creating these graph structures with these nodes, is that you can combine the noise in different ways. It doesn't always have to be additive. It can be subtraction or multiplication and other approaches. And you might even have different nodes interpret the parent node differently. So a node with multiple children, well, each node could interpret what base noise provided by the parent, interpret that differently and combine differently. And so this opens up lots of possibilities for authorship. In terms of the approach that I used for the homework, I haven't even fully explored everything or figured out everything that's possible. So that, I guess you could sort of think of it as a pro and a con of this approach. It does make a pretty powerful tool in terms of flexibility, but it can also be at times overwhelming and difficult to understand or to develop an intuition in terms of authoring, especially if you have something in mind to make, rather than just randomly exploring and see what interesting things you can make. If you go in with a specific plan, it's sometimes difficult to pull this off. But It's overall, it's fairly computationally efficient approach, simple approach, and you with tiling, purl, and noise, you can make a, a nearly infinite terrain that tiles with a terrain system. And so, if this was properly and fully tied into Unity's terrain system, tiles could be just dynamically generated as the player, let's say, walks to the near the edge of a terrain square. Then the next square in the grid could be requested, and the terrain generated based on whatever the offsets are as the tiling occurs. So this could support runtime procedural content generation. Now, the next thing that you can do once you have this terrain is that you can consider applying these simulated natural processes like we discussed previously. So this would involve perhaps multiple iterations of these geological and weathering effects that would be applied to the base terrain. So once you generate your rule-based terrain with a hierarchical rules about combining purl and noise, you might want to add some effects that are related to, say, fault lines, or the way water runs over a surface and it erodes over time. And so depending on what your needs are for your procedural content generation, you might apply some or all of these different approaches that we will look at with a high level here shortly. But doing this, it can give a more natural end result, but it comes at a cost of additional computation. So this might impact, say, real-time, runtime procedural content generation, and so that could possibly be something that would have like a negative impact on your game, and maybe that would not be worth the trade-off, and it might be, and it might also depend on whether you're creating your terrain at design time and then storing the entire thing, or generating it. But first, we could consider faults. So this is really a pretty simple approach. You simply identify a fault line, and then anything on one side of the fault line is raised or lowered, and then vice versa on the other side. And it can be a fairly small amount. Often this will be done in conjunction with other effects that would be running. You might apply the faults many times over many simulation steps. So this particular figure shows after application of hundreds of faults, and not mixed in with other approaches, such as like the effects of water, for instance. But this might work well for especially integrate with other approaches. Then there's thermal erosion. So this is based on the observation that common types of granular substrate, like a soil or sand, will tend to bunch up in particular patterns with certain slopes, and so this is just something that happens like incrementally over time. So you can run this at multiple steps, and it would require identifying where in your terrain you have these common substrates. So if you don't have like volumetric data, the simple approach to do is to simply identify an altitude band. So this would mean you're looking for a range of heights. So maybe You would avoid really tall structures because that would suggest it's made out of hard stone. So you wouldn't apply the process there. And maybe you wouldn't apply it at the lowest levels, but maybe a certain band that you would say would be maybe a little above sea level, but not mountain, the height of mountains, and then could apply this. You could also, if you have biomes identified, you might have different types of soil defined. Like for arid regions, you would have a different soil type, so probably sand. But if you have soil identified in a biome that has lots of like foliage, plants of some sort, you would expect maybe the root system to restrict how quickly this thermal erosion process would occur, and so you could adjust accordingly if you're modeling that sort of information. Hydraulic erosion is perhaps one of the most compelling weathering effects that we might apply, especially given that the rule-based approach for combining Perlin noise is going to have limited ability to allow an author to create the sort of detail and structure that you can get from hydraulic erosion simulation. Unfortunately, this is one of the more expensive weathering effects computationally that we might want to apply. It involves breaking the world up into small pieces and considering small amounts of water being placed around the terrain and modeling how the water moves. So this is a finite element method approach, and it involves iterative simulation. So we have to place the water in the environment. This would be by some sort of rainfall modeling, and then the water flow needs to be calculated. So water will be affected by gravity. It will tend to accumulate in different cells, and then like a voxel sort of structure, and then based on the accumulation of the water, we'll have some simulation rules that approximate the effects of the water movement, picking up soil. So that would be taking away from the height map, and then we would need to track the soil that's being moved as part of these finite elements, and then being dropped later as, say, the water changes velocity or reaches a lower energy state. It would carry the soil from high ground to low ground, or move it along the direction that it's flowing. So as you can imagine, this can get pretty expensive computationally. And it's also something where you benefit from many iterations of it. So while the visual end result is quite compelling, it might not be feasible for some types of terrain generation. So, for instance, if you are generating an infinite or near infinite terrain, and doing so at runtime based on procedural content generation rules, you may or may not be able to run this simultaneously during gameplay without an interruption. All right. So another approach that can be used is altitude filtering. And basically, this just means modifying terrain values based on existing heights that are present. And so there's actually a lot of overlap with the capabilities of the terrain rule, the hierarchical terrain rules, or the directed acyclic graph and the nodes. You can already do a lot of the of what's proposed here. So this is actually from Millington's Game AI book, and so he goes through a number of different examples showing how you can apply different effects to a base like a starting terrain. So perhaps amplifying the relative distances between different terrain height levels. So this can, for instance, bring up plateaus out of a largely flat area with its only, like maybe you originally started with only just some subtle differences in height, but then you can sort of exaggerate certain features. And there's a few other examples. And so a few of those could easily be represented just as mapping functions. Some are more complicated and might require, say, rules that are convolution based so that you can analyze neighbors. But just basic limiting modifications of terrain based on ranges of height values is something that is easy to include in the terrain rules engine approach. So there are other ways we might consider making terrain as well. So we've really focused mostly on rules-based approaches so far. So in fact, there's also the possibility of using cellular automaton. And this is where we have little simple rules applied to like individual cells. So we might have a discretized world built into a like a grid structure, and then we have rules about how the information in each of the cells interacts with its neighbors. And so this can be we have a kernel or a certain set of rules that we apply uniformly across all pixels. The only difference in result is based on the neighborhood of each of the grid cells. And then, of course, the rule-based approach, which we're familiar with from the discussion up to this point, and also from the homework project in the class working with terrain. So the cellular automaton approach is interesting because it's so simple in terms of execution. You just iterate through all the discretized cells that define your terrain. So it could be a height map, it could be voxels. Probably most commonly, though, the cellular approaches are 2D. So building things more like maze type structures. But the advantage is that if you find something that works, and that's really the key here, is coming up with the rules that give you something interesting result wise. If you can find that, then it's very concise definition and can give interesting results. So you're probably familiar with cellular automaton. You've likely seen Conway's Game of Life and perhaps even implemented this in like an intro computer science class. It's a popular early in a computer science education popular project, and it's basically you write or you implement a 2D array, and the 2D array can either have cells that have a like a living value in it or dead. So it's like on or off basically. And then you have rules about the neighborhood of a cell. And so the idea is you iterate through every timestamp, you iterate through all cells, and you evaluate the rules. And so the rules are related are based on the neighboring cells. So any live cell with fewer than 2 live neighbors dies. And the idea here is this, like, is caused by underpopulation. Any live cell with 2 or 3 live neighbors lives on to the next generation. So that's like it's the ideal state. Any live cell with more than 3 live neighbors dies, and that's overpopulation rule. And then any dead cell with exactly 3 live neighbors becomes a live cell, and that's the reproduction rule. So the rules themselves are very simple. It's very easy to write code to evaluate these. So we can quickly iterate over an array, apply the rules to determine what the new value is in the next time step. So you can use similar approaches for terrain generation. You come up with rules that give interesting results. You come up with some configuration to start with, some seeding process. So you populate your grid structure with values, and then you run the simulation, and you're looking for a point of stability where initially you get a lot of changes, the structure grows, creating your terrain, and then it stabilizes to the point where there's just a minimum level of change. And so this is easy to implement. You get very complex behavior from just a small set of rules. It can work well for making your structure, your terrain structures for your game. But in terms of downside is that there's a lot of guesswork. It's hard to engineer something using cellular automaton because of the fact that it is emergent outcome. And so when you have this potential for emergent outcome, the only way to find out what it does is to simulate it. So there's lots of trial and error. It can be hard to debug. So if you have different sorts of initial configurations as part of your game, that you might miss some initial configuration or an edge case, like maybe you have one environment cross over into another, and so there's an interaction there. And if you haven't tested or planned for that, or have some rare combination, that there might be some weird outcome and strange resulting terrain, or perhaps a broken terrain. So it can be a bit dangerous, and it's hard to constrain as well, because the ideal way to manipulate the behavior of cellular automaton is to simply adjust the rules of the system. But doing so can have rather profound effects on the overall result. So you can't really add special case logic to deal with like some one particular undesired output. So you might instead try to add like a watchdog process that oversees and monitors what the cellular automaton is generating, and then try to restrict or block. And so that adds a lot of complexity rather quickly if you're trying to do so. So that from what I've seen, at least, cellular automaton approaches, while they're interesting, it's most commonly applied in simpler sort of 2D sorts of scenarios, more like building mazes, and it's more difficult to scale to larger and more complicated scenarios, or like 3D type of scenarios. That's not to say it's not possible, though. So next up, let's consider how to make Minecraft. And so with the game Minecraft, it's unique, at least compared to what we've looked at so far. We're focused on height maps because Minecraft has 3D, truly 3D terrain represented by voxels. So it has a terrain that's generated by noise, but this noise gives the 3D structure to the terrain. So there's more to it than what a height map provides. Which, even though the end result in a game is a 3D terrain, it's really quite limited because you can't have, say, overhangs or tunnels. And Minecraft is all about caves and tunnels. So we have this the noise source, and it's actually turns out it's a Perlin noise based 3D Perlin noise. It also has a rule based structure. We can think of it as different agent implementations that have special jobs that they have to perform. So it's kind of like specializations in terms of the procedural content generation and terrain creation. A bit similar to the way we've so far seen with a height map based approach of having like special rules for different combinations of noise, and then especially also the weathering of the terrain. So we have sort of a similar approach with Minecraft. So there's agents that deal with like generating the terrain, converting terrain types. So like figuring out where soil is and stone is. And so each of these agents get different opportunities. And so there's this really nice video on YouTube. And this was developed by Ant Venom on his channel. And so, of course, you can go check out his channel, maybe check out his other videos as well. I'm going to show here his little short video he did about Minecraft and how it is actually generated. So there's multiple stages, and at each of these stages we can think of it as different dedicated agents that do these creation steps to create the Minecraft terrain. So I'm going to let this play, and you can check it out.
So, today I want to do something pretty unique. In today's video, I want to visually show you how Minecraft generates its terrain using 4 separate mods, each of which show you a different phase of Minecraft's world generation, starting with the stone-only noise map and working our way to the foliage-filled world that we ultimately see with Minecraft. Unless you've given it a decent amount of thought, you might not be aware that the game actually generates one thing at a time, but very, very quickly. And after spending weeks of trying to figure out how to make the mods required for this video, I caved and asked a friend of the channel, Lukavon, to help me out on this quest. And he had all 4 mods done within just a few hours. What a boss. So with all of the pre-work done, let's go ahead and let's get right into it. Alright, so if you've ever heard me use the term 3D Perlin noise in previous videos that I'll have linked above, then what you're about to see on screen is a visual representation of it in action. When Minecraft generates its terrain, it first starts out with a noise map, which forms the shape of all of the terrain, including hills, valleys, oceans, and rivers. Within Minecraft, this comes in the shape of a world made entirely of stone and water. At this point, no caves of any kind have been generated. One other thing that has been generated, however, are all of the oceans and rivers, which generate on any vacant blocks with a Y value of 64 or less. As you can see, this forms the foundation for Minecraft's terrain. Beyond this point, more terrain elements will begin to generate. After the stone and water noise map are generated, the primary surface of the world itself is formed. And while I originally thought that blocks like dirt, grass, and sand would generate on top of the top layers of the stone noise map, they actually overwrite the stone itself, but without any trees, caves, or foliage. However, caves aren't far behind in the code, actually generating immediately after the surface of the world completely forms. You might notice at this point, however, that ores like traditional ores along with diorite, andesite, and granite don't generate just yet, and that makes sense. If the ores generated before caves did, that could potentially take up a lot more computer power than would be necessary. But as you might expect, however, all ores generate immediately after the cave systems do. So, alright, we now have the overworld without any foliage, and we have cave systems with all of the underlying ores. After all of these terrain elements are formed, Minecraft adds all of the world's decorations. This includes things like trees, tall grass, flowers, and as well structures like the pyramids, jungle temples, ocean monuments, and everything in between. At this point, we are now playing the full and complete version of Minecraft. Obviously, I don't need to provide a mod for this stage of world generation, as everything is now completely done. However, in the description below, I have included the 4 mods that Lukavon has created for this video. The mod that causes only the stone and water noise map to form. The mod that only has the surface with no foliage or caves at all. The mod that has caves but no ores. And finally, the mod that has all ores but no overworld foliage. Beyond that is Minecraft release version 1.12. While I do plan on making more breaking Minecraft videos as soon as I come up with some really solid ideas, let me know in the comment section down below what you guys thought of this kind of video, since it is kind of much different from the majority of the videos that I've been doing. And if you did enjoy this video, then please consider leaving a like on it, because it would really help out myself, the channel, and the video quite a lot. So I hope you all enjoyed. My name is AntVenom, and I bid you all farewell. Thanks so much for watching.
All right, so yeah, I think that's an interesting look into how Minecraft works, one of the most popular games with procedural content generation. So, of course, there, in the case of Minecraft, it needs to be very efficient implementation of their generation algorithm, so that it doesn't make the player wait forever for the initial creation, and then as the player moves past those initial boundaries, to not have a big impact on the game. So overall, it's really pretty simple. It avoids some of the issues that you might otherwise want, like some of the weathering type effects are not generated. Instead, there's more abstract sort of processing that takes place, but it still results in compelling gameplay, unique environments, and it is been a very popular product and entertaining for a lot of people. So to close out discussion of terrain generation for procedural content generation, the one really important step that we haven't discussed yet is the issue of placing terrain features. So once you've generated a terrain, you need to add some interesting things so that you don't just have a barren moonscape. Ideally, you would want to have objects such as trees and bushes and rocks or other sorts of decorations that would be placed. And so that's certainly a critical step, and it merits its own lecture topic that we will go into in the next lecture. So we'll discuss ways of placing objects that that can work well in a terrain, and of course we want to be able to do this efficiently. So we will stop there. Hello. In this lecture, we're going to look at object placement for procedural content generation. So we've previously seen how to create a terrain, and so we might want to automatically place objects on that terrain, such as trees or bushes and rocks and so on. So we will need to come up with a way to do this such that it is aesthetically pleasing, that we don't have objects that are overlapping when we place them, that we can control the frequency in which they're placed, perhaps based on some desire to have maybe lots of a certain object in one part of the world and then fewer as you head in a certain direction. So like maybe a gradient of the frequency that they occur. So we're going to look at a few different ways that we can do this. All right, so probably the simplest approach we could take to placing objects, well, we've already learned about random number generation, how we can create a seed, and from that seed generate values. And for multi-dimensional values like a 2D position, let's say, we could just call the random number generation twice, get two separate floating point values, and immediately we have a spot that we can place our object, and then repeat that as necessary to place lots of objects. And if we do that, it'll work. We'll get a spread of objects placed randomly, but there is a tendency for there to be clumping, and this appears very unnatural when you're like, say, placing trees or some other natural features. It doesn't look natural when you place things in this way. So there's a tendency to have kind of an almost uniform separation, not like a grid, but like the average separation tends to be pretty consistent with natural features, like for a given density. Like you tend to, like trees in a forest all tend to be a certain distance apart, even if it's a very dense forest. And then if you have features that are more sparse, they still tend to be spread out pretty well. So we would like to come up with a way to sort of create that sort of separation. And one popular technique is to use a Halton sequence. So a Halton sequence relies on leveraging coprime numbers. And you do this to generate a fractional sequence of numbers, and this is repeated over many steps. And so the idea is like you might have a number for the X term in a 2D number, and then another number for the Y term. And so that'll be the base for the generation. And so these two numbers would be coprime, and that would mean that the common divisor between the two numbers is 1. There's no other common divisors between the two numbers in order to be co-prime. So by leveraging this, you can come up with a repeating sequence of numbers to generate a lot of values, say over a 2D space, and it will create generally nice patterns that have pretty good separation, avoiding a lot of the clumping problems you would get if you were instead just directly calling random number generation. So the way it works is you pick a controlling number, like you pick one of your numbers, and so this would be maybe an example for, say, like the x dimension of a 2D position for placing objects. So you start with that number, and you then generate fractions within the range 0 to 1, where n is the denominator. And so you find all of the values going up in integer sequence for the numerator. What are all the values that work? So you try, for instance, 1 over 3, then 2 over 3, and then by the time you're to 3 over 3, you're at 1, so that value won't count. So for 3, when we first start off, the only valid numbers within that range is 1 over 3 and 2 over 3. So then what you do is you go to now a smaller fraction by taking your controlling number and to the power of 2. So it is 1 over 9. So now what you're going to be doing is you're starting with 1 over 9, but you're still counting by a third. So you're going to just add that to the sequence so far. So currently we have 1 over 3 and 2 over 3. Then we're going to have 1 over 9. And then counting by thirds, we would then have 4 over 9, then 7 over 9. And we can't add a third to 7 over 9 and stay within the 0 to 1 range. So we've run out of that sequence, but we're not done with the 1 over 9 or the 9 version of the controlling number yet. So we're next going to try 2 over 9. And so you start with 2 over 9 plus, so that'll be the next in sequence. Then you add a third. You end up with 5 over 9, add a third again, 8 over 9. And then you continue on, but you always skip over any values you've seen before. So when we get to 3 over 9, that's actually 1/3. We've already visited 1/3 before. So we would skip that and then would go to whatever the next value is that hasn't been already in the sequence. And so you just keep continuing that process, going to the smaller and smaller fractions. So it's a little confusing in describing it as this example, but the algorithm for the implementation is much more straightforward. So here is the code for just the one dimension is on the left, what was just described. The algorithm, you can generate the values with that little bit of code. And then, of course, to do the 2D, you need, well, two separate coprime bases or controlling values. And then you need to know where in the sequence it is, which is the index. So the more values you would need, the index would be increasing. So you just keep grabbing one after the other, generating these values. And so this can be pretty useful for creating these sorts of patterns that are good for procedural content generation and low overhead. Now, if you get to where you're using large control numbers, that can result in artifacts, and that's especially the case in the first few numbers. So if you have, like, say, 1 over 13, and then you're counting up in those first first few values that you will have some artifacts in terms of the placement. So it's typical to skip over those values, and possibly even beyond that. It'll generally settle down to like the visual patterns that you see will settle down if you skip over certain values. And in some cases, you might even count by k. So like if you say the index value, you would skip ahead by this value k, where k is also coprime with the in value. So Millington says in his book that it's rarely needed to do the skipping by k, because often you'll just be using a small value of for your controlling values, for like your x and your y value will be pretty small, and you can get variety just by simply starting with with some different index. So you might jump ahead by 100 or something like that, and then that will allow you to get some variety. So a Halton sequence is neither random nor pseudo-random. It's actually considered quasi-random. And this is because it's the same every time. It's not seeded. You simply get different results through the control values in the offset. And it does have some characteristics of like a random distribution in terms of the patterns of values that occur, and that can be desirable in some use cases. So yeah, it's not actually a random number generator, but it gives you information that sort of has a flavor of randomness in terms of the distribution. Now, another approach that can be used for breaking up the clumping that you can see with object placement is to use a Poisson distribution with a grid lattice. So if you have a space that's subdivided into, say, grid cells, you could, based on the desired density of object placements that you want to generate, you can figure out, well, what's the number of objects that should go per cell to achieve the desired density for the overall area. So if you have that situation, you can just say, we'll go, you can visit, iterate through each cell, and then within that cell, use the convention of random number generation to come up with your x and your y. And then you just you place your 2 points within, or if your target was 2, you would place your 2 points within the cell, and then you go to the next cell and place 2 more, and then just keep going through every single cell placing your 2 points. So that's a naive approach to this strategy. It will give improved results in terms of limiting the clumping that you'll see, especially with more sparse numbers of features placed. It'll get them spread out in a fairly uniform way. The problem with this approach is when every cell is guaranteed to have the same number of points, it creates a bias towards the edges of the cells. So when you have adjacent cells, there's going to be a tendency to have more points close to the edge, the common edge of adjacent cells, than the interior of the cells. And this can be noticed by your like, say, if this is a video game, those playing your game would notice that there's this weird change in density near some place in the environment, and they'd probably be able to see basically where this grid structure was in the game. So like your trees or your grass or whatever, they would see this weird change in density. So the solution to this problem, to get rid of what you see near those boundaries, is to vary how many points there are placed in each cell. And the way to do that is to use a Poisson distribution instead. So rather than say that every single cell has exactly the same number, instead that number we're going to say is the expected number of points, or the average or mean. So we might say that on average there's 2 or 4 or whatever the number is points per cell. But the reality is it can vary. So there is a chance that even if the average is 4, there's a chance that there'll be 0 or 1 or 2 or 3 or 5 and so on. And so if we assume that this is a Poisson distribution, then we can use the equation shown in the slide that will tell us the probability that the given number of points k is what actually occurs. So if we're trying to figure out if, while the average is 4, what is the possibility that we actually get 5 points in the cell, well, we can just plug 5 in for k. Lambda is our expected value of 4. And then that's all we need. So it's lambda to the k power, e to the negative lambda power, and this is over k factorial. So you can plug this in for k equals 0, k equals 1, 2, and so on. And you could keep on going forever with a Poisson distribution. There's a greater than 0 chance to infinity, but it becomes incredibly small chance for to go much further than the mean. So what you actually want to do is only go until the probability of some value m is below a threshold. And so rather than calculate all possible values to infinity, we're gonna stop at some point and say, all right, well, we're just never going to even consider the possibility of these extreme numbers of values. And then so you can replace that particular value, p of m, with 1 minus all of the values that you've seen so far. So so you have like your p of 0, p of 1, p of 2, p of 3, and so on, up to p of m minus 1. Now, if that p of m is very small, then 1 minus everything up to right before it, you're probably going to end up with a value that's like a fraction of 1. It's going to be probably pretty small, but we're cheating a little bit. We're saying the p of m value is slightly more likely than is actually the case. So all of these values together will add up to 1. So the p of 0 plus p of 1 plus p of 2 and so on, all the way up to p of our special version of p of m that catches the whole tail of the distribution. All of that will add up to 1. So what you do is you take all those values that you just calculated, and this generates some thresholds. So it's like a 2-part threshold that we have, and it breaks up the range of 0 to 1 in floating point. So we have for the possibility of there being 0 points would be from 0 to whatever p of 0 was. So that is a range of values. And then we have from p of 0 to p of 0 plus 1, and then p of 0 plus 1 to p of 0 plus p of 1 plus p of 2. So each of these will be these increasing values in the range of 0 to 1 And what we can do once we have this list of threshold ranges is we can generate a random number with a random number generated pseudo-random number generation algorithm. And then we can find, well, which of these m different ranges, where does it fall? So our random number is generated in the range 0 to 1, and we know all of our test thresholds are in the 0 to 1 range. So we'll find a particular level in this threshold where the number we generated fits. And so that determines how many points we generate in our cell. So once you've gone through all this trouble and set up these thresholds, you can quickly determine how many points to generate in each cell. And so if you go back, look at this figure here. So when we would generate our points to go in a cell, each cell has the potential to be different. It'll tend to be right around whatever we set our lambda to, whatever that value is. And that's the expected or the average amount that we believe to be in each cell or want to be in each cell. But the fact that we're using the Poisson distribution, that those variations means that we're relaxing some of the pressure, like statistical likelihood of there being too much information along these edges. So even though we're generating in this discretized form, we'll minimize the potential for any artifacts to show up because of that. All right, so the next thing we can consider is, so far we've only been talking about points and not considering that many of the features we place, we really want to consider the area or the volume that they take up. So for instance, if you're placing a tree in the game world, you don't want to place another tree right up against that tree. So we've discussed a little bit about avoiding clumping, but there's still not a guarantee with these approaches so far that we won't occasionally get two trees that are like right on, almost on top of one another. So we would like to be able to offset at least by some sort of collider radius, and that's typical in games, is to define the shapes of objects. Even 3D objects tend to have a kind of a circular offset defined by like a cylinder or a vertically oriented capsule. And so we might want to say that a tree is, in terms of being placed on our terrain height map, that they're separated by a radius, and that defines a circle around each tree. So that might be the extent of the branches or the trunk of the tree. So we don't want the trees to get any closer than that radius. So right now we don't have a way to deal with that. So one thing we might consider is to use Perlin noise for feature placement. And this is something that you might consider if you've already implemented Perlin noise for, say, terrain generation, and have some ability to maybe manipulate the noise with maybe shaping or mapping functions. And other sorts of like hierarchical rules that we've looked at before. So it's a bit of having a hammer and looking for a nail. If you already have something that works, that you might, to save time, perhaps just use that for our feature placement. In fact, we already have a bit of feature placement in terms of the mapping functions can create feature-like manipulations of the terrain height map. So I've got a picture here. This is one of my terrains I generated where I'm placing lots of little craters and rocks in the environment. And you can see that these are, well, they're not infinitely small points, and but they're all well spread out, and that's based on setting a scalar for the Perlin noise, so that we can like zoom in or out on the noise. And we know that because it's gradient noise, it's frequency limited, so that we can expect to only see the frequency information like periodically over the dimensions of our terrain, which is going to be based on whatever the scalar is set to. So if you're using a shaping function to take like lower frequency information and then create higher frequency information at the minima or the maxima, then we can have some guarantee of separation between these objects. So that works well for these sort of terrain features. And we might even use it for other sorts of object placement, like separate 3D models, like trees that we would want to drop in the terrain. You could potentially use Perlin noise for that. You would just have to determine a point measurement of where these minima and maxima are. So you could write a mapping function that would just give you a single point, and then so we could just collect the points from the mapping function. You could do this with image processing techniques. So this would be perhaps some thresholding, and then perform what's called an erosion. So once you've thresholded, you'll have like lots of little circles or blob-like shapes from the Perlin noise, and then the erosion will shrink down those blobs over a few different passes. It's a fairly efficient operation, but you can shrink down these thresholded blobs down to single points, and then it's just a matter of walking through that. It's basically an image. You walk through the image, and then according to the coordinates where you find these isolated points, then that would map to where you place your features. So I don't believe that's typical in uses of procedural content generation object placement to use Perlin noise in that fashion. But I think certainly that would be something that would work. Now, probably much more common, especially looking at various books and documentation about procedural content generation for object placement, is Poisson disk. So this is a fairly simple algorithm that considers placing objects in an environment, taking into account that they take up space, so like an area. So it approximates all the objects as being circles. And so you start with, say, the space that you're going to be placing your disks or your circles. You either start from the middle of the area or pick a random point, and then you place the disk, and then from that disk you start picking random directions offset from the current disk and placing new disks. And so each new disk that is placed gets added to an open set of disks that we might visit later. And so we keep iterating on the current disk, trying to place these offset disks. And again, they'll be limited range, so they can the center of the next disk can be no further than 2 times r plus k. where r is the radius of all of the disks that are being placed. So a distance of 2r would be the closest that two disks could ever be to one another in terms of measuring from their center points. So 2r would just be half the width of one disk and then half the other to get from one center point to the next. Now we can also add this k parameter, so 2r plus k, and that is like a density controlling parameter. So if we have a large k, then we can place the disks more sparsely. So you keep placing these disks, and once you've exhausted all the disks that can be placed, you set the current disk to no longer being in the open set, and then you randomly select another disk and go through this same pattern of trying to generate new disks, and you just keep working your way through until you've exhausted all of the open set of disks. So it's a really pretty straightforward algorithm. In most of the challenge of implementing this is the test for overlap, and so in order to streamline, it's often coupled with some sort of space partitioning, like breaking the world into a grid lattice and then determining neighboring cells. So a circle, that overlaps with particular grid lattice cells will mark them as already being occupied, and then so that can streamline the testing, so that you're not having to do as complicated a test. Now you might want to be placing objects with variable density too. So not just the fact that we're trying to avoid overlap, but we also want to have varying object placement according to, say, a density map. And this density map, it might come from a noise source like Perlin noise. So perhaps in the Perlin noise would provide areas of the map that are where we want lots of features placed, but then there'd be parts of the Perlin noise that are a low value, and we would want fewer features there. So we have this like range of density. Additionally, you can do this as just a man-made sort of process or handmade process, where someone just paints the features onto a density map, maybe like a spray paint type tool. So this would be similar to how objects get placed in like the Unity terrain editor. So this density map, once you've got it either generated or handmade, you can then use that to be an input to our whatever algorithm we're going to use for our object or feature placement. So it'll look at the density map and decide whether a feature goes there or not according to matching with the desired density. So a value of 0 would be, like if we're placing trees, that would clearly be no trees where the 0 is. And a value that's somewhere between 0 and 1, well, we probably have some intuition that intuitively that means that as you go from 0 to 1, we're going to get to more and more trees that are placed. And a value of 1 is maximum density of trees. So there's this issue of, well, what does maximum density mean when we're talking about trees? And we'll go back to that in a couple slides here. But we know that we're representing our objects like our trees with these circle colliders, And we know they can't get any closer than their radius to other objects, like so with a Poisson disk. In fact, we could use Poisson disk for this purpose of variable placement. We just need to consider as we're selecting an active disk and placing these new disks. Well, we just need to figure out, well, what is the density in that area, and that we could map to the offset radius. So, like adjusting the k value, or just the overall, or the radius of how far out are we looking for placing these disks. And so that will allow us to attenuate the density of placement just by varying that value. Now, the downside with the Poisson disk is that it's not necessarily good at dense packing. So if you're especially concerned with the nature of whatever content you're placing, that you want it to be packed especially dense, well, the Poisson disk algorithm, just how it selects randomly through like random number generation and places features, you can end up with some poor choices for placement that aren't very densely packed, but don't leave room for additional disks. And if the algorithm was more aware, could have left room for like maximum packing. And so this is shown in the figure here with the blue disks. Say maybe these are the disks that have been placed so far with the active yellow disk. And you can see that there's two spots that could almost hold another disk, but they've already been kind of cut off. There's these partial gaps that if we had just slid one of the blue disks a little lower, perhaps it would have left room for an additional. And so you can have these sorts of problems with the Poisson disk approach, and that means that we can still attenuate, we can still adjust the density by mapping these this density parameter to the k, or the offset radius, but we might not get as dense as possible for a full density value of 1. Now, another thing we can consider with Poisson disk is tiling. So it's pretty common in games with procedural content generation that you don't want to generate the entire world. You want it to go on indefinitely, and the way to deal with that often is a tiling scheme. So say the player is moving through an environment. They might walk for a certain while, and they're going far enough that new content needs to be generated. And so this can be done through creating a discretized space, like a grid lattice sort of structure. And as you approach the edge of the generated content, you might generate new content and perhaps unload content you're getting further away from. So as you get close to the edge of the map, you load in new tiles, and as you get far from other edges, those tiles start to be unloaded. And if you do this right, just the nature of our random number generation that is seeded, we can recover that information again. We can regenerate the procedural content just by recognizing where we are overall relative to these discrete tiles. So we can load in tiles that we've visited before, and they will be recognizable, at least in terms of the terrain features, and hopefully also the object placement and other aspects of gameplay as well. So if we were to use Poisson disk, we would like to be able to tile. And so this is not something mentioned in Millington's book. I think it is covered in some other places. There's probably a number of different strategies to deal with this, and it is something I think that is probably important for a lot of games. And so this is just something that I considered would be a good solution. There's probably some others out there as well. But one approach I think that you could take is to for each tile that is loaded, well, you can figure out a contracted boundary. It's like an expanded geometry that we've discussed in previous lectures, but we're actually offsetting towards the interior of our tile. And so if we have that offset be the radius of our discs, then we can guarantee that any disc we place remain entirely within the bounds of the tile. Now, if we only stopped there, we would be able to easily load new tiles, and we wouldn't have to worry about any, say, trees that are generated overlapping with trees of the adjacent tile. So that would be a good thing. But let's say, we're Legend of Zelda, Breath of the Wild, and have like this kind of approach, and Link is up on a mountain looking down on the forest. Well, you're going to see these obvious tiling because none of the trees overlap across these tile boundaries. Or even if you were down in the forest and just happened to like look down the line, you would notice, well, there's this perfect gap separating all the trees, but I only see that gap, periodically as walking through. So that wouldn't be a very good solution. You would want to have trees that kind of partially overlap these boundaries. But the challenge is that you're loading and unloading these tiles. So how do you know where these trees are from like adjacent tiles when you're focused on generating content for the current tile? So one thing that I think would work is to keep track of these overlap regions. So you generate all your disks using the normal Poisson disk algorithm within your tile. Any disks that are entirely within the contracted boundary, those you have in one set, and then any that spill over past that contracted boundary, meaning the center point is beyond those extents, that means part of the tree overlaps into an adjacent cell. So you could figure out where each of these trees generated that go beyond, but still have their center point within the current cell. That would still be a requirement. But any that go beyond, we would put into one of 8 different sets. And so this would be like up, down, left, and right, and then also top left, top right, bottom left, bottom right corners. And so you have all those, we'll stick with trees. So you have all those trees identified. Keep them each saved in a separate set as candidates. So when a cell is loaded, only the trees that are entirely within the contracted boundary are immediately rendered. And then if an adjacent cell is loaded, then you go through a process of negotiating, well, which trees in the overlap are used, because both cells that are neighboring, or both tiles that are neighboring, will have candidate trees in the overlap region, and some of them might overlap with one another. So you have to go through a negotiation allowing each to decide, well, who gets to keep the trees in the overlap. So you have to be very consistent with this because we're depending on random number generation. I want to make sure that we always have the exact same approach every time. So we need some way to determine rank between tiles. And so we might do this simply by looking at, well, what are the X and Y positions of the cells? Maybe the center point or the bottom left corner determines those coordinates determine where each of the tiles are, and then we can just make a comparison. We might say that the cell closest to the origin wins, and we first check X and then Y dimensions. So once you've determined the tile that is the higher of the ranks between the two that we're comparing, we can then go through a process. Well, that the highest ranking tile gets to pick one of its trees within the overlap region and say, all right, I'm selecting this tree. And then you see if it collides with any of the overlap candidate trees from the other cell, and all of those get removed. And then the lower ranked tile gets to then pick, if it has any left, it gets to pick one and place it. And then you continue this process of pruning away any trees that that are blocked from forming. And so this should be a consistent process and like a repeatable process for determination, because you're always determining rank between the tiles in a consistent way. And you always start, each cell always uses their same seed to generate all the trees, both the ones that are within the contracted boundary, but also the trees that are held aside that are in the 8 regions mentioned before. So you always have the same trees, and then the negotiation deciding which trees actually get finally selected, that will be consistent as well. So that would be a way that you could hide the boundary. Now there might still be some problems with tiling with Poisson disk. I haven't fully explored this, but I think perhaps if you have a very large K value for like especially sparse layouts, there might be a spot where it's difficult to get a tree to place right in this sort of the common area between adjacent cells. So if there's a tendency for the algorithm to basically decide that it's exhausted all possibilities for the active disk, and have never placed any in these common edge areas, then you might still see some visual effect there. So there's probably a bit of tuning that would be required in order to get this to work. And again, I'm pretty sure that others have thought about this issue of tiling with Poisson disk and how to best address it. Back to the issue of the density of placement. So again, it's very clear what 0 means in terms of density. There's nothing there, and it's easy to put nothing in terms of object placement. But as you approach 1, well, what does that mean? And you could just decide, well, it's arbitrary. It's just best effort. We'll say it's whatever our algorithm can do. What maybe Poisson disk, whatever the densest that it can place objects on average, that's what we'll call 1. But if we really wanted to strive for the densest possible, this becomes a disk packing problem. So in terms of like the study of algorithms, this is something that comes up. It's like, well, how can you determine what the best or most optimal disk packing is? And so this is a really hard problem. It's I believe, except in certain special cases, that it's not solved in for general cases. It's usually only solved for like a small n, where n is the number of disks. and it gets a lot more complicated when you have like a variable number of variable size in the disk, or as n gets larger, even placing in a like a uniform structure like a square, that it can still be quite complicated and perhaps like algorithmically intractable to solve. And also, in cases where there is like easily determinable optimal packing, that tends to be like highly uniform. So, like say, fitting circles into a square, they might be so uniformly packed in the optimal sense that like you would never want to use that for placing trees unless you wanted it to look like it was a tree farm, so where they're all in perfect rows and columns. We really want them to have more of a like a natural sort of look in most cases with our procedural content. Um, so what I'm getting at here is that it's probably we're never going to be able to just come up with this straightforward algorithm that gives us the best solution. So very much an AI sort of a problem that we're getting at. But we might be able to do better than Poisson disk in terms of density. And so there actually is another approach, and this was documented in a GDC, I believe it's GDC presentation for the game Horizon Zero Dawn. And so this game has some really impressive procedural content generation, especially related to object placement. And you should definitely watch the presentation. I'm not sure how to pronounce his name. I believe it's Jop von Moyden, but he goes through in his presentation how the entire system works, and it's all in the GPU. So the GPU handles figuring out where objects are placed based on some rather complicated hierarchical rules for placement. But one of the fundamental pieces of the placement is that they have a pre-computed disk packing tile. So it's a repeating tile, and this tile is coupled with ordered dithering. So dithering is an image processing, or has its origins in image processing, especially mapping color spaces down to a reduced color space, like say for newspaper print or early computers like CGA and EGA graphics, when you wanted to represent lots of colors but you only had just a small number of colors to work with. So the dithering worked well there. And so dithering makes sense when you have a high resolution density map, and you're mapping it to these discrete on or off sort of, yes, there's a feature there, or no, there's not a feature there sort of decisions. So by having this predefined circle or disk packing tile, you've already determined something that is approaching the maximum, most optimal packing possible, and then you couple that with the dither testing. So you're testing the probability from the density map. You're testing that against the thresholds that are assigned from the ordered dithering approach. And then that allows you to be able to handle these smooth gradients in changes in that define your object placement. So this does, while it does have this random structure, it's a repeating tile. So I've got a picture of the tile. This is actually from the GDC presentation that was given for Horizon Zero Dawn. So this gives an example of their circle packing. And you'll notice if you look really carefully at the edges where the circles show up, you'll see like if one is sort of jutting out over the boundary, well, there's kind of a recessed area. It just go from like the top fold over to the bottom, and you'll see there's a perfect little spot for that disc to fit, and go left to right and see the same thing. And you'll also notice that these discs, they have the very tight packing, but it's in no way uniform. So there's lots of sort of random little variations. And I believe this was accomplished through slight variations in radius, and then perhaps also allowing some overlap. And I bet there's some other little tricks they used as well to not allow any sort of uniform structure to be present. But this gives us a tile, and then each of the discs in the tile have assigned a dither value. And again, that is used for the purpose of mapping. Let's see. So, oh, sorry. Here is this image here is an example of the dithering. So the top right image there. So this is showing that underneath we have black representing a density of 0, and then white would be, well, you can't really see it very well, but white is in the areas where we have all the discs placed. Now this is very uniform looking here, just to make the example simple. And then we have progressively more spaced out discs as that we transition through the gradient. So this is useful for like the edge of a forest where you want to have trees that are very dense, and then they kind of taper off as you transition to a meadow, for instance. So that again is used in Horizon Zero Dawn for their placement. All right, and so I've attempted to, I've been working on this off and on for a while, trying to recreate their tool. Unfortunately, they don't give a lot of details in their talk about this particular aspect. They say that they implemented a circle or disk packing algorithm, that they made it where it tiles, and they also describe briefly their dither values. So I will go through a little bit describing what I did, and I'll have a separate video where I show a little interactive demonstration. So the first thing I did was to implement my version. I suspect the Guerrilla Games folks may have done the same thing, but I made a wraparound coordinate system so it works like asteroids. So if an entity moves off the left side of the screen, it gets mapped to the right side. So I have a bunch of spheres that are restricted to a plane, and this basically becomes my disks. So since they're restricted to a plane, they're effectively disks. And this was implemented in Unity, and the 3D physics is more capable than the 2D physics based on Box 2D, I think is the name of the other library. So this was more robust, and I could still get 2D constraints out of it. So that's what I went with. So I used contracted geometry to determine where these spheres are, or the disks. And also, let me step back and I'll say that the disks are not all of uniform shape. I wanted to get some introduction of non-uniform structure. I think there's still some room for improvement there, but did get it's much better than if they're all exactly the same radius, but I think there might be some other little tweaks to make to get it anywhere close to as good as the Horizon Zero Dawn tile that I showed before. So then I've got point gravity in the middle, and so all of the discs are being pulled to the center of the tile, and so they're all bumping against one another and being pushed apart by the others. If a sphere goes partially off beyond the contracted dimensions, it will begin to overlap with the other side. And so as soon as it's past that contracted boundary, I spawn a copy or a doppelganger that begins to appear on the other side. And so you can see there are orange discs. The orange ones mean that they are associated with a red copy of itself, but approaching from the opposite side. As soon as I do that, I change the center of gravity to be between the two. And there is a joint that connects the two by an offset. And there's only 3 degrees of freedom. Actually, I guess it's only 2 degrees of freedom because it's in 2D. There's no twisting allowed. So that way other spheres bumping against one or the other can't cause a torque and twist them. They can only push them up and down or left and right. And then they can possibly cross over from one side to the next, just like in asteroids, and in which case, if it fully crosses over, then it'll swap the orange and the red. And eventually, if it somehow moves to the interior, it might switch back to green, meaning that it's no longer got a copy, and then I just delete the copy. So that actually ended up being easier than I thought it would be to get just the disk packing with the physics working. So that was pretty easy to do. There were some issues like trying to get the full square to be filled. And so I played with like just clicking and dropping extras. So I maybe start with a pool of some number of spheres. And then the corners wouldn't be full, so I would fill them in by basically kind of painting them in with the mouse. And if actually a better approach I found was to just scale all of the spheres with hotkeys. So I'd hit like plus and make them all slightly bigger until they began to fill out. Or if there's too much fighting between them, I could shrink all the sizes. That might be better if you want to have, let's like say, exactly a power of 2 number of discs, which would probably be desirable rather than just adding more and more with the mouse clicking. So yeah, I think that works pretty well. There's some room for refinement. So next we get to the issue of creating the dithering values. And so if you look into how dithering works, you create specifically it's called order dithering. And the reason it's called order dithering is your dither values are in order. So let's say you have a range from 0 to 1 of values. So the number of dither values you will have will be like the number of pixels or the number of disks you have in your dither map. So originally this approach was used with pixels with uniform structure. So that's depicted with the M's. So the 2x2 and the 4x4 and then 8x8 are shown. So that the 2 times 2 gives you 4 total dither values. And so that these are shown in that first example, but the probably more interesting is when you get to the 4x4. So you get 16, but you have to place all these dither values, and so you divide up your range of values. So if it's if your range of values you actually want normalized to like a 0 to 1 floating point scale, you would just divide 1 by 16 and you would count by those fractions. But you want these fractions placed in this repeating pattern as far from similar values as possible. So if you notice, in this case, we don't have the 0 to 1 scale. We just have the 16 values shown. But like if you look at the for the matrix with a 4 by 4, you'll see it starts in the top left with 0. Then it places the next value as far as it can get away, keeping in mind that this is a wraparound asteroid-style coordinate system. So the furthest you can get in this case is not going to be the bottom right corner, because that would actually be right next to the 0 diagonally. So instead, you see where the 1 is placed, and then 2 and 3 and 4. And you'll notice this pattern, and it's kind of a similar pattern for the 8 by 8. So if you look where the 0 and the 1 and the 2 are, it just looks kind of very much the same, but just spread out. And that is because you want these dither values to be as far as possible apart. The reason that you're doing that is because each of these values are their test values. That it's a threshold. And so you overlay your dither map on top of the image that you want to remap, like say colors. You overlay it, and then you test each pixel what its actual like high definition color is. You test it against each of these thresholds to see where it whether it's above or below, and then that determines whether you turn on or off the pixel, and it gives you the dither pattern that you're looking for. The problem that we have is that, well, this Bayer pattern, which there's an algorithm for, and you can pick like an arbitrary size matrix, and then you easily generate the values, and they'll have this optimal spread. Well, one thing is that it can give these unnatural patterns, and that's shown in the figure here, like especially the grayscale here. You get these kind of weird hash sort of patterns. You can see it also in the color. So it's not as natural to use. But we also have this issue, well, how can we generate a similar pattern with our disks that are kind of, they're all densely packed, but they're not perfectly aligned like pixels are. And so what can work in that case is blue noise. And so with blue noise, it's very similar to the Bayer matrix in that we're going to be placing each of the ordered dither values as far apart as we can. But we're going to do that just by a brute force evaluation of all of the disks. We'll pick one, say randomly, to assign the first value, and then we want to place the next disk as far as possible away. So we have to take into account this asteroid style overlap distance. So whatever's the closest distance across any of the edges, or just directly across the middle interior of the square. So that whichever is closest going in any direction is what we're going to use as the distance. So we're going to take into account the contribution of every disk assigned so far to any unassigned disks. Well, what is the intensity, like the contribution of intensity from all of those assigned disks to any given disk? And the one that is the darkest is the next one to receive assignment. So it ends up being a pretty straightforward algorithm. You again, randomly, you pick a disk, you assign the first in the ordered sequence, increasing. So we have, so like if you have 64 disks in your tile, you would divide 1, because we have the range 0 to 1, divide by 64. So we have that first value So we randomly pick a disk to assign that first little incremental value. Then we go through all of the disks and find, well, okay, which one is the darkest based on the contribution of that one disk so far. So all disks we're going to cache, we're going to keep track of the accumulating intensity being shined upon them. And the way we determine that is we use a Gaussian distance. So this has a smoothing effect. So that the contribution of any given assigned disk to an unassigned disk will be based on the distance plugged into a Gaussian distribution. And that the variance will be a fraction of the furthest, like whatever the furthest distance you could be apart is. So that would be like going from one corner of a square to the middle would be the furthest that you could ever have two disks from one another, taking into account the overlap. And so some fraction of that will be the ideal variance for the Gaussian filter. And so we use that to remap each of the distances. So that would mean that closer neighbors have more contribution of intensity than further neighbors. And so you keep iterating through and you just keep finding, well, of all of the disks, which one is the darkest? And then once you've got a new darkest one, you add its newly assigned intensity, which happens to be its dither value. And you just keep going through, and then you end up with all of them assigned. And so this figure, or this picture shown here shows in my code after this has been applied, and also it's tiled. The tile is no longer present by itself. It's actually repeated several times, so you can't even see where the tile is. And all of the dither values are mapped just from like black being a value of 0 up through white is a value of 1. So there's a grayscale range. And so it's really hard to see any structure here. So this blue noise, it has minimal low frequency. So you don't see any distinct large scale features. And there's no distinct high frequency bands either. So it's really hard to see anything other than some randomness with some small scale high frequency structure. So that's gotten to the point where we can now perform our dithering. And so this is an example taking that same pattern that we just saw. That now all of the disks have been turned white, just so that there's not any optical illusions. But there is a gradient here where to the far left and far right is a very high probability or density rather. And when we perform the dither, we basically, for each disk, look at the center of the disk as it overlaps with the density map. So whatever the value of the density map is, in this case, it's just evaluating a function that I wrote of the distance from the center line. But that gives me the density. And then I test that against whatever the dither threshold is. And if I go back to this slide, the dither threshold is the value between 0 and 1 that corresponds with the color that you see, or the grayscale value you see here. So black would be very close to 0, white would be very close to 1. So whatever the density map value is, if it's very close to 1, it would very likely be above a low value dither threshold test. And so that will toggle the disk to be turned on, but if it's below, I turn it off. So that explains why you see very few disks in the middle, and it progressively increases in the likelihood of seeing a disk as you go out to either the left or the right. So the way in which you would use this is you determine the size of your features in the environment. Say you have a tree with a radius of maybe 10 meters or 5 meters, something like that. So you would scale your dither map repeating tile. You would scale it such that the discs that make it up have the same size or approximately the same size as your object. You scale it up to be tree, so each disc is tree size. So that's going to make your tile take up a lot of space of the terrain. Then you separately have a density map. And again, this might be defined by something like Perlin noise, and it might be defined by something that a level designer has painted themselves. And so when you have the overlap of the two images, or the dither map with the disks and the density map, you sample probably with nearest neighbor, just whatever the closest density value is. You test it against the dither threshold, and that determines whether the tree gets placed or not. So if your density map has lots of close to the value of 1, then you're going to have super tightly packed trees. And they're super tightly packed because we use the physics-based disk packing to get them all very close together. And once you come up with all of these positions for placing your objects, you might want to apply some small perturbation, like just a little wiggle with random values. And that's acceptable with trees and other foliage, because you're probably not going to notice if the limbs of the tree are interpenetrating other trees. It would just probably look like the limbs are slightly tangled, and most people wouldn't notice. But just the little bits of movements will help reduce the game player ever recognizing that there is this repeating structure and applying the tile over and over. If you want to do the same thing with small structures like little tiny bushes or grass, you would just scale the texture, the dither map, appropriately. It's not really a texture because you have these non-uniform disks in it, so it's more of a coordinate system, and then you're mapping this hierarchy of all of these disks to that. But once you scale appropriately, again, you're just applying it to your density map, and it will tell you where to place the features. So be sure and check out the Guerrilla Games Horizon Zero Dawn presentation on procedural content generation, and they'll go through their implementation. There's a lot of special cases and other details that they share. Actually, one more thing I want to talk about is still something that that Guerrilla Games worked on. So this is when you have mixed object placement, and so this might be a case where you want to place a mix of objects, say like different types of bushes or grasses and things like that. So if you have these multiple features, well, you don't want them to overlap. So you could maybe use separate density maps. Certainly would make sense. You want to have maybe have different levels of density for each type of thing. You might also want to have some hierarchical rules to generate dependent maps. So you might be able to say like multiply two density maps together using like Boolean type logic, so that like maybe you could restrict certain features or favor, say, plants that need a lot of water would be near riverbanks, and then have other plants in meadows. Not put a tree where a boulder is, and that sort of thing. However, we might not want the overhead of maintaining these separate density and dither maps for every single feature, when there might be just minor variants in say, the type of flora that we are placing. So we perhaps need a different solution, and so we could combine these the thresholds for these different objects in terms of the dithering. So now the thresholds have now a minimum and a maximum, and the object selection is determined by the density value in relation to these threshold ranges. So let's see. This is what it looks like in the example from the Horizon Zero Dawn presentation, is that they now have a combined dither map where for each sample point, which is again set by where these disks are in our tiled packed disk setup, but rather than have a single dither value test, we have these ranges of thresholds, and so that way you can only ever trigger one. Now, if they didn't use this approach, one challenge that they face is for, I guess, GPU performance reasons and memory utilization. They only use, I believe they say in the presentation, they only use a single packed disk tile. They don't have lots of them. They generated exactly one and reuse it for every single type of content, no matter the size or scale that is applied. And so if they overlap things that happen to have the exact same disk radius, they would have the issue that if they were separately testing the thresholds, that these objects would try to place things in exactly the same place. And so that is one of the key reasons why in Horizon Zero Dawn they use this approach with a layered dithering. All right, I think that covers everything in terms of our look at object placement. It is a pretty important problem, and something that can take a lot of effort to get it just right, especially in terms of fine tuning and like special rules if you're trying to get lots of different assets to work well together. So like this mixing of object placement, there's probably you can probably quickly get to where you can place things, but then the fine tuning and getting everything to look just right, that I believe there'll be a lot of effort in the fine tuning to get everything working. Hello. In this video, I'm going to demonstrate my attempt to create an ordered dither map using physics simulation, similar to what is used in Horizon Zero Dawn's in GPU object placers. So the actual dither map was made with a tool external to the GPU work for the live object placement, and same with my implementation. So let me switch over to Unity here. All right, so I've got a project, and it has just a simple little interface. I've got a little tile that will form, and it'll immediately drop a bunch of spheres that are restricted to a 2D plane. Let me start that up. So you can see the spheres, and in the background is the gray region that defines where the tile is. And currently you can see that the spheres do not fill up the entire tile. You'll notice there's some different colors here. So there's green, and then orange and red. So the green circles are entirely within the tile region, and the orange and red are on the edges. So orange are disks that have just begun to cross over to the opposite side. So you can think of like the game Asteroids, where you can fly the little ship off the left side of the screen and pass to the right. So that's happening here. These spheres are being pushed off, and if they go just beyond the contracted boundary of the tile region, offset by the radius of the disk, then it will appear on the opposite side in red. So like this orange sphere, well, we'll think of it as a disk here, that matches with the red on the opposite side. And so you can see how it, just barely is over on this edge. And so the red is intruding just barely on this side. All of the spheres are under a effect of a force that's pulling them to the middle. So that controls the grouping. I have some hotkeys that I can hit to expand the radius bigger or smaller, and you can see the effect here. So I can shrink them or make them bigger to try to get them to all fit in, and I can also click and spawn new spheres. There seems to be a bug on this computer not recognizing my single clicks correctly. Let me see if I can use a mouse instead of a touch point. Yeah, it still seems to be a little messed up on this, but it's normally supposed to be one click makes a single sphere. So it makes it a little harder to work with, but I primarily do the size scaling, and that would actually be ideal if you're trying to maintain a certain number of spheres. And so once you get to a stable configuration that has good coverage, I can go to the next phase. I hit spacebar, and it begins placing the dither values according to the algorithm for generating blue noise. And so what's happening is that for every, you start with a randomly selected disk that has its the first value in order of the dither values. So you take the range 0 to 1, divide it by the number of disks that you have, and that tells you the increment value to increase by as you go through the dither values. And so you can see the values that are set. I have the value mapped to a color, so grayscale. So right now they're all very dark colored that you see being placed. And so the algorithm works by, after the first initial disk is assigned, then all the disks are evaluated to see what contribution that single disk makes to it. So you can think of it as kind of like a light that's given off, and then the further it is away, the less influence it has. And so once you figure out the amount of intensity that kind of spills over, and this, you actually use a Gaussian function to do that. So it has kind of a blending effect once you add up all the contributions. But after all unassigned disks have been updated with a running total, and you don't need to do a weighted average, by the way, meaning you don't have to divide each every time. But since you're making just relative comparisons across all the disks, you can drop that step. So you're just figuring out which one has the lowest intensity of all, and then that will receive the next value. And you just continue this process on and on. And so it's going incredibly slowly now because I have intentionally added a delay. But I can decrease the delay. I'll speed it up some. You can see you'll just keep placing these. Again, it's always updating a tally for each unassigned disk to see what the full contribution is, and then every time there is a new disk that has the lowest value every iteration through assigning a new one. And so you can see how it does a good job of spreading out the different intensity values. And I'll speed it up some more here. So yeah, I sped it up to full speed. And as soon as it finished, it immediately went to the next step, was doing a test tiling So it placed a tile up, down, left, right, and then the corners as well. So you can't see the tiling, it's hard to find any sort of distinct repeating pattern. I mean, if you look really carefully, you can probably find where the repeats happen, and there are some small scale patterns, but not any like low frequency patterns, which is ideal for what we're doing, and is a characteristic of blue noise, so that there might be some small scale patterns that appear, but none will small, which means a high frequency, but there's none that really stand out among any of the other similar frequencies, and there's no low frequency, meaning a larger scale structure that you see. And if I hit spacebar again, it will use those same positions, but switches the color just to all white, so that you don't see, so you're not thrown off by the different colors. We really just want to focus on the gradient here. So the center line of the screen is the lowest probability of there being an object placed. So we've transitioned to an actual test mode to perform the object placement. So think of this as like a forest. So we're placing trees in a forest according to a density map. So the density map will have probabilities from 0 to 1, 0 being the lowest probability or lowest density, and therefore meaning no trees. And then we transition all the way up to 1, which would currently there's just a gradient. It's not all the way from 0 to 1. It's I think it's 0 to 0.5 now, but I can hit some hotkeys to change what the full range of the gradient is. So I'll start by going down first. So I'm decreasing the maximum value out to the left and right, and you'll see that as it flattens out, we will see fewer and fewer. So we can just imagine that we have a density map that we're using. So it's like it's applied to the same space, say like a terrain. We have the density map. It overlays the same area that we're overlaying these tiles of the ordered dithering. So we just look under the center point of each disk to figure out the probability at that point, and then that we test that against the threshold of each disk. So each disk within the same tile has a unique threshold, and so that's what we're testing against. And so if it passes the test, we can draw the tree or replace the tree. If it doesn't pass, then no tree goes there. And so that's going to vary according to the density map. So you see I can keep working my way down. And this is very low density here. And then I'll work my way back up all the way. So I'm just spamming this key here to increase. So the same gradient is always in place. I'm just multiplying times a value that's getting bigger and bigger towards the maximum, which is 1. So once we reach that, it should be a density of 1 on the far left and far right edge, but it'll stay low probability in the very middle line. But quickly there's a gradient that transitions to the left and right. All right, so I've hit 1 now. So again, far left, far right, you can think of, like if there is an image here, we would see, if we could see a visualization of the density map, it would be just a smooth gradient of what we see of the disks. So it would be like, look like black was spray painted down the middle and then just gradually transitioning from black to gray onto white to the left and right. And then so we have a dithered effect of that density map with where these disks are placed. So the idea is that now that this tile has been calculated, you would save it out maybe as some sort of exportable format, maybe like a JSON file or something of that sort that would tell you the positions of each disk, and then that structure could be imported into your procedural content generation for your algorithm for the purpose of object placement. And so that would be tiled on whatever surface that you want to use the procedural content object placement. You tile it over the surface, scaled such that the radius of the disks roughly matches the radius of whatever the type of object you want to place. And then you just go through the dithering test to make this comparison. So the probability the density map versus the thresholds in the ordered dithering tiles. And so that'll give you your placements, and that is, of course, it is tileable and it's repeatable, and you can use it. It's efficient, so it's good for real-time procedural content generation, such as we see in Horizon Zero Dawn. So hopefully that gives you some insight into a method that can work well for the purpose of placing features in a procedural content generation environment. Hello. In this video, we're going to continue looking at procedural content generation. In particular, we're going to take a look at grammars used to generate our procedural content. All right, so we've previously seen rule-based procedural content generation, such as the rules that we use to shape and sculpt our Perlin noise. And this was very powerful, at least for that purpose. However, that approach is insufficient for making guarantees about certain gameplay features that we might desire. For instance, navigable connectivity, meaning creating an environment such that our game player can traverse from one location to another. We might be able to make some rules that tend to favor navigability, but it's very difficult to make any sort of logical guarantees about the nature of our environment. We have this very emergent sort of outcome. It's difficult to predict exactly what's going to happen. You just have to play around with it, try it, and see if you get the results you want. So what might we do if we want to have more direct control over the content we generate, at least in terms of some sort of guarantee? And so this is where we can use grammars. And the technique of using grammars can be seen in games such as Spelunky that connects several different template rooms together to create small dungeon-like environments in 2D that the player can explore and face randomized challenges. But it's all done in such a way that there are guarantees about connectivity, but furthermore, that the character that the player controls can actually navigate everywhere that they need to. So in terms of climbing and jumping and moving around, if you're not careful with other techniques, you might generate something that, say, is aesthetically pleasing, but that you can't actually make the jumps, or you don't have ladders and other means of navigation available to you. So this approach of generative grammars, it originates from Noam Chomsky's study of languages way back in the 1960s. And he came up with this concept of components or symbols that are interpreted with rules. And this defines how the combinations of symbols can be put together. And you can apply it to lots of different problems, language in particular. Words can be placed together in sentence structure according to grammar rules. You might also apply this to content generation in a video game. For instance, you might have a generative grammar that builds body shapes for aliens. So the rules would be specified by a designer, and it would allow for generating different types of creatures. In Spelunky, each level starts out as a grid, and then each grid cell gets filled with potential templates. And these are all pre-designed by the game designer, Derek Yu. And so the templates get filled one by one, and then later templates are chosen according to rules about how the templates can neighbor one another. So I got a few more details in a from a YouTube video that I will play a little bit of, and I recommend that you check out the full video on YouTube. I'll have the link in the notes. Oops. Let's see. All right, let me get this started. I'm going to jump to a particular spot here.
So, every level in Spelunky is generated by a script that starts with the same basic shape and size, 16 rooms in a boxy 4x4 grid. The first thing the script does is pick a random room from the top row and makes this the entrance. It will then randomly place a room to the left, right, or beneath this room. This process is repeated from room to room, and if the path hits the edge of the level, it also goes down until we get to the lowest level. When it tries to go down once more, an exit is made. Every room on this main path has openings to the left and right, but rooms where the path drops also have exits on the bottom, while the rooms you drop into are given exits at the top. What you end up with is a guaranteed path through the level that you'll always be able to get through without using ropes or bombs. The other rooms are not on the critical path, so they may be open or they may be walled off depending on their design. Next, each room is randomly given a template. Derek Yu handcrafted a number of room designs with different layouts for rooms where you drop down, rooms you land in, corridors you run through, and rooms not on the critical path. But these templates are not set in stone, and parts of them are randomly generated. Sometimes entire chunks of tiles are plastered on at random. This means that while you might start to see familiar setups, they will always have their own unique quirks. Next, a script checks every tile on the map and rolls a dice to see if it should place down a monster, some treasure, or another object. Again, it's not entirely random. Gems and crates are more likely to appear in spaces surrounded by walls, and enemies generally don't spawn in cramped spaces. And everything is weighted, so a level isn't filled with fire frogs or crates containing jetpacks.
All right, so that was a little look at how Spelunky works. So that is from the YouTube channel, I believe, the Game Maker's Toolkit. So I recommend that you check out the the complete video for some more details about how Spelunky levels are generated, and also the impact on gameplay. So the nature of the gameplay, the fact that it's not something that the player can memorize, it means there's an entirely different strategy to becoming proficient at the gameplay. So it demonstrates a type of gameplay that's really only possible with procedural content generation, and that's I think a large part of the appeal of Spelunky. Next up, we're going to look at a different type of grammar called an L system or Lindenmayer system. So this is a type of grammar where each piece of content changes every time step. So you have a starting point, and then you keep replacing a symbol according to some rules. So you will have variables, constants, and then rules that you apply. And then there's also an axiom, which is the starting point. And so you can select between all of these to come up with different ways to generate your grammar. And then you also additionally need something that interprets the end result, which is basically reading the sequence of symbols that are generated and following the instructions that are implied by the symbols. So we might have an example of building a tree-like structure. So we could have variables 0 and 1, and these represent some structure, and we have constants such as brackets or parentheses. And so these cause a behavior like a rotation. And then we'll have our starting point. So from that starting point, we have the symbol 0, and then there are rules. So there's one rule that shows a mapping of the symbol 1 to a new configuration. And then there is another rule for 0 and mapping it to a new configuration. And so the 0 could be replaced with a 1, and then a 0 inside of braces, and then another 0. And so you can keep applying this until you get to some terminating condition, and then the end result can be interpreted by, say, a rendering algorithm that understands the deterministic messages that are part of the grammar. Here is another one. This is from Wikipedia's page on L systems. And so this particular example has variables x and f, and constants plus, minus, and brackets. So the axiom or starting point is the symbol x, and then there are rules for how the L system generates. So the f means is interpreted by the algorithm that draws the plant. So it draws forward, and then minus means turn left 25 degrees, plus means turn right 25 degrees, and x is not something associated with the drawing action. It's just like a placeholder, and so it's used for facilitating the rules. And then the square bracket acts like you might expect like parentheses to work. So you're saving state so you can remember what the state was as you go down to like the sub branches that you're drawing. And then so you can go back to where you were before in terms of a position. And so this can drive a very simple set of rules, can drive some pretty complicated and natural looking fractal plant type structures, and you can use it for lots of other things as well. So grammars are nice, that they have good general usage possibilities. Lots of different types of content can be created using different types of generative grammars. You can get very high quality, often have these sort of natural look to them, especially things like trees. It's very accessible. It's easy to work with. You don't necessarily need to be a programmer or a computer scientist to work with these. So you can have authoring tools where the ability to write grammars is something that lots of people could quickly pick up. And they also tend to be very fast, just the nature of the symbol processing. Downside, though, puts a lot of burden on the designers. A lot of time will be spent configuring and tweaking to get just the right results. It's kind of got this emergent sort of outcome. They can be hard to debug once you start to add some complexity to them. And it's really just observing the outcome of using them doesn't really, it's not a true validation that the problem is fixed. You might have just moved from having a problem in one area to now a new area, whatever change you applied. So any change to the rules affects all possible outcomes, and there might still be some edge cases that could be a problem in the future. So grammars certainly can be, especially L systems, are commonly used in things like trees and other types of plants. You might also use them for things like avatar generation, so the different body features, or aliens, different types of enemies. So games like, I believe it was Spore, so it had the different creatures. You could perhaps you have a generative grammar for that. Some types of level generation are well suited to grammars. It seems like 2D games especially can work well. And I'm sure you can come up with several other examples that would work well. Yeah, so grammars are a pretty important aspect of procedural content generation. You'll often see it coupled with other approaches. So perhaps it would be a component of terrain generation for generating the different types of plants that you want to place in your procedurally generated world. Hello. In this video, we're going to continue looking at procedural content generation. We're now going to consider the use of search-based methods. So this is the idea of having a large space of possibilities, but instead of specifying exactly how we want to generate results from one of those possibilities, such as with rules-based approaches or with grammars, generative grammars. Instead, we will focus on some means of evaluating parameters within a space and just use a search to explore the space and evaluate what we end up at. And that is going to drive our procedural content generation. So what we are going to be able to achieve is We're not going to spend a lot of time authoring because we're going to, again, avoid creating rules or grammars. Instead, all we'll need to do is define heuristics and fitness functions. This will allow us to score the quality of a move. Like as we explore search space, we might have a heuristic to favor one choice over another, or perhaps the end result we can evaluate with a fitness function. This will give us a score of the quality of the result. So we don't need to understand as much about exactly how we will get there. We're just concerned about the end result and whether it is good or not. So if you have a means to perform that evaluation, then that means you have a means of comparing different possibilities within a very large space. So there are different approaches that could be taken, including heuristic search, hill climbing, simulated annealing, and genetic algorithms. So we might use depth-first search in some situations for procedural content generation. This is probably most popular to use for generating mazes or similar types of structures, perhaps something like a city with different roads that connect in different ways. So you can use a depth-first search to explore a discretized space, such as a grid. And as the depth-first search is applied to the space, and different options are considered, your algorithm can place walls and just continue on until some goal is reached. If there is a goal, it might just be that you want to fill the space. So you can generate a path until you run out of room. Of course, you can build all those walls. If there are any unexplored paths, you can just branch from nodes that were never explored initially, and just expand so you have all these different branches and sub-branches that go off and completely cover the space. And so that gives you a nice maze-like environment. You might apply certain types of constraints that might have some impact on the shape of the paths, maybe that they don't get too close to where there's walls that have already been defined. So you can have you can impose some separation through a heuristic. You might pre-populate the space with obstacles that will basically not be part of the frontier. And so the search algorithm is just not allowed to explore those areas. It could be reserved areas for gameplay purposes or some other reason. So there's a lot of different things you can do in terms of using depth-first search. There's also some similar sorts of things you can do, kind of getting away from depth-first search specifically, but things you can do such as figuring out connections between rooms, like by applying a minimum spanning tree algorithm to find a way to connect rooms. So this can be a useful way to generate content for your game. So if you are trying to generate procedural content just by using search to try to optimize some metric, well, the key here is you need that metric. So you have to be able to define fitness, which is the fitness of the solution is like the quality of the solution. And so that's really, it's going to vary. It's going to depend on the domain of what you're attempting to achieve. So you'll need to have a well-defined way to do so. That might be by trying to analyze like some aesthetic features in the content generated. It might have something to do with gameplay, like ensuring that that there's a connected path for the player to get from point A to point B. So there's different things that you might need to do. Most search-based optimization strategies use this concept of the energy of the system as being the metric. And so we need this way of calculating energy and change in energy related to where the search is going. So you have some discretized representation of the state space or search space, and when as this exploration occurs, the search algorithm is applied. The change in energy is positive if you're moving like in a good direction, so it's a good move, and then it can be negative if it's a bad move. And so we need this way of computing and then being able to make these comparisons. So one simple approach is to use hill climbing, again, provided that we have this means of measuring the fitness of the parameter space that we're exploring. So what are all the knobs and dials in terms of how we can manipulate our content generation? But we're specifically looking for the procedural content that maximizes the fitness. So if you can evaluate at any different parameter space configuration for what generates your procedural content, if you can make that evaluation, then you can look in the neighborhood of any particular point. So that would be like some combination of like a continuous parameter space. You can evaluate a point, and then you can see what direction it's going by looking in the neighborhood, perhaps involving a derivative, and that gives you a gradient. And then you can just follow this gradient. And if, depending on the nature of your parameter space, you might have a nice smooth gradient, and it's really easy to just follow the direction in whatever is the appropriate the appropriate direction. Like if you're trying to maximize the fitness function, then you just follow so from whatever initial point you evaluate, you just follow the gradient until you reach the peak. And so that is the ideal configuration that you should select. But a lot of problems, unfortunately, don't have this nice monotonic sort of gradient. A lot of cases, you might have local minima, local maxima sorts of issues. And so this is where you might need to use some other strategy, beyond just looking for a gradient to follow. So there are various approaches. I'm not going to get into a lot of detail, but it's covered in, I believe, the intro AI class gets into a lot more detail. But you might use, for instance, a momentum-based method. And so in this case, you have an analogy of like say a wheel or a ball that's rolling in the direction of the gradient, and it can pick up speed. And if you reach a point that you're not sure if it's a local minima, local maxima sort of situation, well, the ball will have picked up a lot of speed, and therefore it will search beyond beyond the peak proportional to the speed that it's picked up. And of course, in terms of the algorithm implementation, you remember the best result you've seen, but you will go looking further beyond that point. And the idea is that you'll be carried past any small speed bumps, so to speak, in terms of like local minima or local maxima. And so that can be helpful, provided you have like a higher level gradient that you can follow, and you can sort of skip over these little local disturbances. Another approach is with hill climbing is that you can trial multiple initial points rather than start with just like picking a single one and then looking for a gradient. You can instead try several, and hopefully you can find, if not the best, you can find something that is close to the best. Kind of similar to that is the approach of simulated annealing. So it's inspired by annealing in metallurgy. So this is, you can think of it as, say you have hot metal that you've formed maybe from a liquid into a solid, and as the metal cools, connections will be formed between the molecules, but they might not necessarily be the optimum connections in terms of relieving stresses in the material. But as the material cools, while it's still hot, connections will form and break and form and break, and so that if this is done if the metal cools at the right rate, it will sort of fall into a natural pattern of relieving stresses and molecules connecting in sort of an optimal or close to optimal fashion. So sort of inspired by that physical process, this can be implemented in an algorithm. So in terms of searching a parameter space, you might have, well, so you have this fitness function that you can evaluate, but you don't have this. You don't have this. Your algorithm doesn't have this overview of a graph like what we see here in the visualization. All it can do is evaluate points and figure out from the points evaluated what the best it's seen so far is. So the question is, well, what's the ideal points to explore? And so that exploration process can be driven by the annealing. So you're picking a neighbor based on some probability t, and that is this probability is based on how long the algorithm has been running. So the idea is that you start off very hot, and then you're cooling off, and so that you're going to have a quality score for the neighbor, and you're going to be making decisions about whether or not to move in terms of the explored position according to this probability. So as it cools over time, you're going to be transitioning from exploration to exploitation as it cools. You'll tend to stay in the same position or closer to the same position. When you're hot, when the algorithm is in the hot phase, it will be more likely to jump around in very large swings, large changes in the position that is being evaluated. So with with the simulated annealing, just at a high level, the algorithm is going to work by, start at some randomly chosen initial state. Then you're going to work through some maximum number of steps. The temperature is going to be dependent on the number of steps. So again, it's going to start off hot and it's going to cool off over time. And we're going to select a new state through a random process, looking at the neighbors of the state, and whether or not we transition is going to be according to this this probability. So when the temperature is high, the probability of switching states is going to be much more likely. So that's the exploration. And as it cools off, that's going to become less and less likely the further the randomly selected new state is from the current state. So that's going to mean that the most likely new states to evaluate are only going to be ones that are in the progressively smaller and smaller neighborhood. So we're going to go from quickly sampling like all over the parameter space down to progressively smaller and smaller. And so this will allow refinement. So the exploitation. As it cools off, the only positions that are likely to evaluate as passing are going to only be in this ever shrinking neighborhood. So you'll be able to find the highest position in like a local maxima sort of situation, at least within that neighborhood. And so this can work pretty well. Oh, and also as this process is continuing, you'll want to keep track of the very best sample that was ever seen. And then so the final return will be the best that was ever seen. Just in case, through the random chance of jumping positions that you jump to a worse position to explore. So this can give good results. It's very dependent on the temperature function. And so that's going to be domain dependent, and you might even have to tune it a lot for whatever specific problem that you're working on. In the worst case, if you don't have a good temperature function, it's basically going to be a random search, kind of similar to the non-monotonic hill climbing example we saw before, where you just have lots of just selecting lots of random points to explore. Another way that you can search parameter spaces is with genetic algorithms. So this is loosely inspired by the theory of evolution. So sometimes it's called evolutionary search. And it tends to be a popular approach just because I guess it sounds kind of enticing to have AI that has evolving solutions. The basic way the algorithm works is that you have a population of configurations. So this is the exploring of the state space, and you check the quality of all of the solutions, and from that you're determining, well, which of the population to keep, and then of the population that you are keeping, then you go through this sort of natural life cycle sort of approach. So there'll be some number of mutations in the population you can think of as like genetic mutations. And then there is a reproduction phase where some of the population will share their configuration. So this is something that has some characteristics of exploration and exploitation. So when you have mutations, this gives some probability of randomly replacing a member of the population with a neighbor. So you're replacing some parameter within. Maybe you have a whole bunch of different parameters, and so one of them will be changed from whatever its current value is to another value in the state space. So this particular new value is probably not present in the population, at least for that one specific parameter. And so you have this entirely new configuration for this particular member of the population. But you also have crossover. And so this is where you have lots of configurations, lots of examples of the search space in terms of all of the parameters. So you have 10 different parameters. You might pick to swap a parameter with another in the population. So you end up with new configurations for both, but individually the parameters were present in the population before. And then what happens is once you have all the mutations and crossovers, there's a reduction in the population. And so the population will grow according to the mutations and crossovers. You can keep your previous examples, then you evaluate all of them, and then you just pick with the ones that have the best score according to fitness, and you just keep repeating this process over and over. So again, the mutation is exploration, because this is where you're picking up parameters that were likely not present in the population, and the crossover is exploitation, because this is finding among the population you'll tend towards finding good isolated parameters, and then as many generations have this crossover performed, you'll find the right combination of those parameters. And so the idea is that you will get these increases. And if you don't have nice smooth gradient in terms of the fitness function over the many parameters, you still have a chance to like jump past local minima, local maxima because of the mutation. So you might still jump from being stuck on one narrow range for a particular parameter or combination of parameters. You might eventually discover a good combination. So the pros of genetic algorithms is the reduce authorial burden. So it's a bit more than with hill climbing, but it's less than, say, the generative grammars or the rule-based systems that we looked at. It's also genetic algorithms tend to do a good job at finding a combination of parameters that gives close to the global optimum fitness. The downsides of genetic algorithms are that it takes a lot of experience to pick and to balance the mutation and crossover, and the fitness function can be challenging to implement as well. And then lastly, there's this notion of genotype to phenotype mapping. So the genotype is the representation of the actual features in this like parameter space form. And the phenotype is like, well, what's the actual content? And at least in the context of procedural content generation. So the features might be, say, the placement of artifacts or some properties of the levels or terrain that are being generated. So how can you map those features to some sort of parameter space that is defined in the genotype? And so that sort of mapping is not always intuitive. All right, so overall, with search-based procedural content generation, the positives for the search-based approaches that we looked at, it allows designers to specify high-level desires in terms of heuristics and fitness functions rather than low-level content authoring or rules authoring. Downsides, designing these evaluation functions can be very challenging, and you'll often find that many developers will prefer just to go ahead and use the generative grammars approach rather than trying to figure out all the intricacies of developing these evaluation functions. Hello. In this lecture, we're going to continue looking at procedural content generation. In particular, we're going to look at constraint satisfaction and wave function collapse. So we've previously explored rule-based systems, such as the rules that we discuss for controlling Perlin noise. So we saw how we can get this nice emergent sort of output, often can give interesting results, but it's difficult to control the output. In many cases, you're best off just playing around with different rules. And if you see something interesting, taking advantage of it, as opposed to having a very well thought out design in mind that you're trying to very precisely create in terms of your procedural content. You can't always pull that off. There's also generative grammars. This can create high quality output. The author can have a bit more control, but it does depend on expertise in terms of authoring, some experience in designing the components and the rules. And search-based techniques can be pretty powerful because it cuts back on authoring burden. You don't need to design any sort of rules or generative grammar. You just need to be able to define a heuristic or fitness function, and then of course also have a searchable representation, perhaps involving discretization. But that can be unintuitive and difficult for many designers to work with. So we might consider a new approach, a bit of a hybrid of some of the techniques we've seen before, and that is constraint satisfaction. It's also sometimes referred to as constraint solving or constraint propagation. It's similar to search. In fact, it has an element of searching to it, but instead of a heuristic, designers give constraints. And so these constraints are facts that must be true in the final output. So whatever the end result of the constraint satisfaction or the propagation of constraints, that must be held true. And so constraints can be authored or learned from an example. So with a constraint satisfaction problem, we have as input a set of variables, and a set of all values that can go into the slots, and a set of constraints that relate slots to each other. And the output is all variables are filled with a specific value. So a trivial example would be a name generator. So you have variables such as first name and last name, and then values would be a list of names, and the constraints would be that names cannot start with the same letter. That would just one example constraint. You might have some others as well. Maybe there's some other initials combinations that are not allowed, or whatever else you come up with. Maybe if you had a middle name also, you would want the gender, the most common gender, to match with the first and middle name, perhaps. Those sorts of things. So if you have a large list of names, well, there's lots of possibilities for any of the variables. So when you start off, you have for each slot, you have like potentially a huge list of valid values that can go in each slot. But if you pick one of the variables, like you pick a first name, well, then there's a constraint that's imposed on the last name. So as soon as that first name is picked, like if you pick Jeff with this particular rule, then you would have to exclude Johnson and any other last name with a J. So you actually would keep track of that in terms of the logic. You would cross off or remove from a valid set for that variable. So initially, all variables have a list of all values that could potentially be used. And then each update, from one of the variables, you just arbitrarily pick what it's going to be. So this is the collapse. And based on the constraints, well, you sort of expand out from the value that was collapsed, you expand out the constraints. Which other variables are affected or impacted by that collapse? And that's going to be dictated by the rules or whatever the constraints are. So you're going to remove from the surrounding variables whatever the possibilities were that they did have are now going to be reduced according to the constraints. And so you continue this process iteratively over and over, collapsing a variable. And so it's generative. You can, as long as you're like driving this by like random number generation, you can just like randomly pick a variable, collapse it by picking a specific value, propagate the constraints. And so that's going to control your content, and it's going to force combinations of variables that meet the author's requirements. So if you've ever played Sudoku before, that is a game. It is gamified constraint propagation. So you've got the different constraints about like rows and columns and what is it, 3x3 groups. So you've got rows, columns, and groups kind of all superimposed onto one board, and you're given a few clues, which you can think of as constraint collapse. And from that, it's your job to do the propagation of the constraints. And so that can be, they're designed in such a way that that's challenging to do. But you yourself might randomly pick a value to apply to, say, some cell, and then you will propagate. And the idea is you either look for a valid board, or more likely you're picking a value that you expect to have a very shallow sequence to an invalid board configuration. So you have a constraint or a set of constraints that tell you what valid solutions are. So if you can quickly find an invalid solution through the selection of a particular constraint, then then you know that that was like a wrong choice and can scratch it off. Now, in terms of how you play it, a lot of people, when they play Sudoku, they keep notes on, say, a sheet of paper. If they're let's say playing in the newspaper, and it'll be just like what's been described so far with the constraint satisfaction. So you might keep track of all of the valid numbers that a cell could currently take on. So you might say, well, this cell, some particular cell, it might be like it could be like a 1, a 5, or a 7, and so you know that those are the only values it could be, and then that'll change as you figure out other numbers. You'll start to scratch off more and more numbers that each cell could be. So it's kind of a similar thing. Fundamentally, this both for procedural content generation and for the puzzles, you're propagating these constraints. So constraint satisfaction is basically a search, but it goes a lot quicker because you're constantly pruning the search space. So if you think of this branching factor of all the different possibilities that any variable could take on, the constraints trim that down considerably so that it's much easier to search through the space for a valid configuration. So you could use constraint satisfaction for something like generating a dungeon room. And so here's an example of exactly what we're talking about with the variables and all the possible values that we're keeping track of all of the valid values in a current step of the search process. And then as we collapse, we're going to propagate constraints. So let's say we have a grid, and right now all of the different rooms in the dungeon are currently possible except for E, which I believe is for the exit. So we have these constraints, like there must be a path from the entrance to all the treasure and enemies. So the E is the entrance. I guess it's the entrance and the exit. It's where the character can go into the dungeon and then start exploring and try to find treasure and enemies to fight. So all right, so there must be a path from the entrance to all treasure and all enemies. There can only be at most one treasure. There can only be at most 2 enemies. Enemies cannot be next to each other. So those are the constraints. So right now, our dungeon, we have a large number of possibilities in terms of like all of these different rooms. It can be 1, 2, 3, or 4. So that would be an empty area, a wall, an enemy, or treasure. So we might pick a particular spot to say place an enemy. So this is just a randomly selected dungeon grid cell, and we're going to collapse down to an enemy value. So as soon as we do that, we can propagate our constraints, and so the one that is relevant in this case is that enemies cannot be next to each other. So you'll notice that up and to the left and to the right, we've removed that possibility of an enemy being placed. So now we only have 1, 2, 4, 1, 2, 4, 1, 2, 4. So next we can collapse again, and we might randomly land on the bottom right cell, and we might randomly assign to be a treasure. And so once that is set, there can only be at most one treasure. So this constraint propagates to every single cell in the map. And so we reduce that possibility 4. And we can continue on with this, maybe placing a wall. And so we have there must be a path from the entrance to all treasure and all enemies. So that will mean that we can't, say, wall off the enemy or the treasure. So that's going to cause some different propagation. So you can kind of get the idea of how this works. It's driven by random number generation, but it's done in this constrained way, so that we get content that meets some gameplay or aesthetic purpose, perhaps. So it can be very powerful for generating content. If you end up with output that doesn't look good, you can just add more constraints. You don't have to consider heuristics with the sort of the interaction that the evaluation can have, and so it tends to be a lot easier to work with. But you do need to strike a balance between being overly constrained and avoiding bad outputs. If you're too constrained, you're not going to be able to generate much in the way of variety. But in general, designers prefer being able to apply constraints. It's a more intuitive sort of declarative specification as opposed to tuning a heuristic or a fitness function. Now, if you don't want to write your constraints, you can instead have the algorithm learn them. And so this is where wave function collapse comes in, and it's become a very popular strategy for procedural content generation in game design. So you might give a little example in terms of a pattern that you're looking for, and then you have an algorithm that evaluates that pattern and basically generates constraint type rules from just looking at the example or set of examples. And so this has been used in different games. There are code examples out there, such as the link provided, and can give a lot of interesting results. So the basic high-level concept of what's going on is you provide some sample input, then the algorithm is going to derive legal patterns from that, and it does so by looking at intersections of patterns to get the constraints. So basically, like for these 2D images, is how can you overlap parts of the image with itself, or tiling the image, but then overlaying them? What would be different valid possibilities when doing so? So the wave function collapse algorithm generating patterns from the sample, then it runs this build propagator step, and then while not finished, observe what is been created. So it's basically doing the classic collapse of like the constraint satisfaction collapse. So when a certain choice is made, then you propagate according to the rules that were generated from the provided patterns. And so this is something that again has become very popular, And it can even be have some interactive like user selection. So rather than just randomly picking, you can have sort of a designer driven approach to building. And so here's a little video that demonstrates this. So what you're seeing is a little interface that applies the wave function collapse. But the collapse is the user selecting, and then the user can decide what are the some mix of automating the pattern finding and specifying the constraints. Once the constraints are applied, you can then iterate on this overall and generate entirely new combinations of tiles to create these like 2D environments. So it's an interesting area for procedural content generation, and it gives some pretty nice results as well. So here's a simple little example where we have our example pattern, and then that can be used to generate an environment. So the collapse involves stamping out the pattern randomly somewhere in the environment, maybe just a little part of the pattern could be stamped. So for instance, it might partially overlap with an edge. And then once it's stamped, you can overlay the pattern with the content that currently exists. And so there's going to be some overlays that don't, where the pattern doesn't fit. So those won't be options, but there will be places it does fit. And then that can be basically is like a rubber stamp or with ink. And you can, as long as you can fit the underlying pattern with some subset of the example, then you can keep stamping it out. So with a 2x2 set of being applied to a 2x2 area, you can align it either directly superimposed or shift it left or right or up or down or up and to the left, up and to the right. And as long as, so you could like randomly select between these different possibilities as you're filling in the content area. And so here, this is showing how you could generate from that simple pattern these different possibilities. So this could generate, say, a background texture, or maybe a cityscape, like blocks in a city, maybe bricks in a wall. So there's lots of things that you could do with the constraint satisfaction. And so the smaller the pattern, you can get these more emergent sort of possibilities. But if you want to maintain more structure, you can, of course, have a bigger example tile. And so that's going to considerably limit what are the valid valid overlap that you might use for that rubber stamping sort of process. So advantages of constraint satisfaction. The constraints are more intuitive than heuristics. It works well for sort of declarative authoring. It's faster in many cases than search due to the nature of how it prunes away possibilities. Though it's slower to generate these due to the propagation. so that could potentially be prohibitive if there is a lot of complexity in that propagation, and of course that would be um, likely the case with the wave function collapse by example, like we've seen. So we saw with the little 2x2 tile how we had all these different possibilities for overlaying. So so that is going to take a while to do that sort of evaluation. Um, but you can, of course, learn the constraints from examples and even have hybrid solutions where you have sort of a mix of learning from example and then fine tuning with the human intervention, like we saw in the one example. Downsides, though, you must be able to represent the problem in terms of formal logic. So you have to actually be able to figure out what are these very well-defined constraints. So this might be easier for some problems than others. If you have very specific sort of gameplay that, like gameplay rules that suggests maybe some straightforward rules like you might find with the dungeon generation. But if you don't have this sort of well-defined rules, then things can get a lot trickier. Hello. In this lecture, we're going to wrap up our look at procedural content generation. In particular, we'll be looking at player modeling. This is basically the idea of understanding the player, and we can potentially, through understanding the player, be able to drive procedural content generation in a way that maximizes the player's enjoyment of the game. So player modeling is not really any one specific technique, but it's a family of approaches for representing and quantifying the player's experience or their preferences with a goal of improving their future experiences. So from the context of procedural content generation, that would mean generating changes in the content such that it better aligns with what the player enjoys doing or how they're doing in terms of gameplay. But outside of procedural content generation, this is commonly a part of analytics. So to collect information about the player, to understand what they enjoy, and this will inform game designers on how to make new game content. So there's two main approaches that you can use for modeling the player. So one is called model based. This is where you have some preconceived notion of what the model is, what the categories are, and you're simply trying to assign a player to these already known categories. And then there's also model free, and so this basically is where you don't know what the categories are and you're trying to define those just through some automated statistical grouping processes. So you're looking for trends that can be correlated, and then if you can find these groupings, those essentially become your categories, but they can evolve over time depending on how you've implemented your system. So with the model-free approach, you're going to start by trying to learn what these types are, and there'll be some sort of statistical analysis through like a regression, and look for how variables relate to one another, and find a set of connections between these different variables, and then once these are defined, they basically become your categories, or these pools of related values or ranges of values. So what exactly might we want to model? Well, it could include demographics. It might be raw gameplay data in terms of different moment-to-moment decisions that are made, stats on game performance like health, number of kills in a combat game, any sort of like accuracy related to gameplay. What are features of the world when actions are performed? We also might have sensors such as like input devices, but it could also be things like heart rate monitors and blood pressure. So there's actually been interest in biometrics for games and driving models. It could also be preference type information that could perhaps come from questionnaires, maybe given before or after, or sometimes even during gameplay. And there could also be aspects of personality, perhaps through a personality inventory type assessment. So some different types of statistics we might have. So in the case of Left 4 Dead, maybe measuring player health, shot accuracy, number of times damaged or killed. Or in an RPG, we might be interested in areas that are visited, time spent exploring, win-loss ratio, time to complete the level, items found, and the items that are used. And also we might consider a platformer like one of the Mario, Super Mario games. So we could look at power-ups that are collected, number of deaths, the nature of what caused the death, like from an enemy or from falling into a gap, number of times performing certain actions like ducking, the amount of time between deaths, coin blocks that are pressed, number of gaps jumped. So the metrics, the takeaway here is that the metrics that you might be interested in are going to vary, and they're going to depend on the game that is being played. So we might consider a game like Mario Kart, where the player is racing on a track, and so we might be making these sorts of measurements, perhaps looking at the player's current place in the race, like first place or second place, and so on. And also we can consider the current state of the world and what the other agents are doing, their the power-ups available to the different enemies. And so from all this information, we can get a position in space and maybe make an estimate of where the player is in terms of the current challenge they're facing, and then maybe even make some guess as to whether they're sufficiently challenged relative to their skill. And so what do you do based on this information? So you're constantly measuring the player's performance and deciding whether they're likely to be bored by their current situation. So in the case of Mario being in first place, far into the lead, you might introduce a challenge by, say, giving one of the opponents a powerful weapon that knocks out the player, and so they lose some time, and so they have to exert more effort to get back into first place or to maintain first place. So you would, for this strategy, you would be modeling the player just through this sort of direct sampling of their ability, maybe calculating some metrics, and then be adapting the game moment to moment. And so this idea is based on this psychological principle called flow. It's by I guess discovered or defined by a psychologist, Mihaly Csikszentmihalyi. Very difficult to pronounce name, but he describes this sense of flow where you're kind of like in the zone, and it's the zone being like you're being challenged in a way that requires full attention, full concentration on the activity, but it's an intuitive sort of concentration. So that you're not overly stressed. You feel like you're in full control, and it's associated with like a pleasant sensation. But it's easy to tip too far to the point where even if you're not outright failing at the task, it's associated with high levels of stress and anxiety. And if you go below that point, it's associated with boredom. So you may have experienced this, say, like driving a car, and it might say you're very bored driving at the speed limit, so you speed up, and you actually feel more engaged driving the car, even though you might be creating a more dangerous situation by going faster. Now, in the case of a video game, you can have the system have a feedback loop measuring the player's performance actually procedurally generate new challenges. And so now, in the case of Mario Kart, there's a lot of fixed content. Really, the only things that can be varied are the power-ups and perhaps the capabilities or performance of the AI agents. But other games, you might actually like generate more challenging racetrack curves or other aspects of the game. It'll really be genre dependent. But flow is a good approach. Is to make some have some hypothesis about what's the right balance of the player's performance, whatever measurements you're making as part of the modeling, versus the challenges that are being presented, and the challenges mapping to some aspect of the procedural content generation. So with flow, the advantage of this particular approach for player modeling and coupling that with the adaptation of the game is, well, it's intuitive and it matches well with the player experience. Disadvantage, though, you need to be able to design reliable measures for player challenge and skill, and that's not going to be possible with all games. You also need to be able to measure very quickly. You have to have a really tight coupling for this feedback loop, and it's difficult for non-competitive sorts of games. And there's certainly games that don't capture or don't have the potential to capture the flow experience. So in the video game design class, we talk about a particular type of gameplay called game feel games, and so those tend to be well aligned with the experience of flow. But there's certainly other types of games where that is not a likely experience. Certainly, like puzzle games or adventure games can be problematic for that. So flow is not a one-size-fits-all solution for driving procedural content generation, configuration, and optimizing for the player. It's really only going to work for certain types of gameplay. Next up, we might consider drama management. And so the idea with drama management is that we're aiming for certain experiences for the player. So with drama management, it's really a nod towards a common user preference for how conflict is presented. So in drama, like in stories or movies, users are, the viewers or the audience, it typically is presented with like a setting or exposition. Then there is a rising action where some conflict is introduced. And then that rising action builds and builds to a climax where there is a process of resolution leading to this falling action, and the story concludes. And often you'll find that drama is broken up into smaller pieces. So you might have I guess progression of the drama is over a period of time that is appropriate for the fatigue that the user or the audience might have to deal with. So like a movie, someone can only sit still for so long and be comfortable. So you have your typical, like all movies have about the same length, and games are kind of similar, but they're not as passive. So this period of time for games tends to be shorter. When especially like action games where the user's highly engaged, there's this intensity there, and the player will quickly get fatigued if they don't have breaks. So this is something that's been discovered by game designers and has been built into static sorts of gameplay experiences for many years now. So in games like, say, Metal Slug's side scroller with just like lots of weapons and enemies, and just wave after wave of enemy. Well, they kind of follow this sort of pattern where the players hit with a challenge, some wave of enemies, and they might be running low on resources, and be really challenging. But then they make it past the climax, and then they get an opportunity to recover. So there's a kind of a cooling off period where they can restore their health with power-ups, maybe pick up some ammo, and be ready for the next wave. So this sort of idea can be applied in an automated way through elements of procedural content generation, and so we can think of this dramatic arc as taking some amount of time. And we have some like target amount of time that we wish to achieve, and then there's some intensity that we wish to recognize and achieve. And so that intensity might be related to the player modeling. And so we might look at something like health levels or the successes in the gameplay fighting the enemy. So the game Left 4 Dead actually uses this sort of approach. And it has this AI director agent working behind the scenes, constantly measuring the player intensity experience. So looking at like the enemies that the player's engaging with, the kill counts, and then so you can imagine that the max intensity would be when the player the character they're controlling is killed. But you can look at other events leading up to that, like taking damage, maybe being surrounded by enemies. So there's different contributing factors that we might be able to measure and evaluate. So the player's intensity score will drop when nothing is happening or less is happening, and we will have this reset at the start of a new stage. You might also consider like waves of enemies where you ramp up to a climax and then come back down again. You don't want to keep the player pegged at the full intensity. Some contrast in terms of gameplay can actually be beneficial to the player enjoying the experience. So this has some similarities to Flow, except we're really aiming for it to kind of ramp up and down again. So we're kind of engaging with the user being more involved, maybe more in that sort of flow experience, but then bringing them back out of it, letting them recover. So there's these three modes that the AI director engages with: the build up. So the AI director will attempt to increase tension, and so again monitoring the player through these different metrics, these live metrics, and then aiming to reach peak intensity for the player. And ideally, you want to do this in a way that's not disruptive to the experience. So outright killing the player can be quite disruptive, pull them out of the experience. So that's something you generally want to avoid, but you can certainly create a lot of tension if the player gets close to that experience. And in fact, some games that aim for this sort of tension might do tricks, like say in a boss fight, when your health gets low, the boss's attacks might start to reduce, or they'll avoid using their strongest attacks, and those attacks won't occur again until the player gets an opportunity to collect some more like health packs or that sort of thing. So there's a potential for a little bit of trickery in terms of the content. Any sort of procedural content generation. And then the last state is the director will relax the tension according to where we are in the timeline for the dramatic arc that we're trying to create. So if we've passed that point of climax, you're likely to start seeing those health pickups pop up, and this will decrease the tension. You might also stop spawning as many enemies and kind of ramping down. And this all can be driven by a finite state machine. So pretty simple AI implementation, though it can certainly get more complicated, and each of these three states can maybe be broken down into like in a hierarchical sense, could end up being fairly elaborate. So the drama management approach for modeling, it is very effective, highly praised. It doesn't necessarily work well for every sort of game, but it matches well with the sort of experiences that players like, and it introduces a new element of strategy in terms of gameplay for the player. Understanding that they just have to get past that climax, and knowing when say they'll have the opportunity to get more health. Disadvantage, though, there's a fair amount of authoring that's involved. isn't as much as player types, which we're about to look at, but there's more involved than with flow, because you have to be able to understand the exactly what this pattern is for making the dramatic arc, and making sure you are measuring the correct thing in terms of the player modeling. And the drama management most likely is going to be implemented with like a finite state machine. So you have those downsides of the implementing and testing and debugging the finite state machine. So now we're going to look at player type modeling. There are other approaches in this. I just wanted to go through one to give you an idea how this would work. So the basic idea is that you have some kind of template categories that you're going to assume you can fit every player into. So one comes from the work originally for tabletop RPGs. So this is Robbins' Laws of Good Game Mastering. And so in this book, there's 5 player archetypes. So there's a fighter who prefers combat, power gamer that enjoys gaining special abilities and riches, method actor, likes taking dramatic actions, tactician, prefers thinking creatively and solving problems, and storyteller prefers complex plots. So these archetypes are most applicable to those that are playing something like Advanced Dungeons and Dragons or some other sort of tabletop RPG. But it can carry over into video games as well, certainly. So one approach you might take using these archetypes is each player has a vector. And this vector represents the degree to which their actions represent these different categories. So each action is tagged with one of these roles. And so that this is, there's a demand on the game designers to categorize all of these potential actions. Each time a player takes an action, you update that value in the vector of the associated roles, so they like increases in value. And then the system chooses reward to incentivize those roles. So it's basically you reinforce the roles that the player tends to demonstrate. And so doing this, it can be useful for understanding the different types of players. It puts a bit of pressure on designers to be aware. Once you have these sorts of archetypes, to make sure that there are interesting choices for every type of player, that there's opportunities to play a game with different mindsets, different ways of enjoying the game, and then being able to reinforce the path through the game that will lead to the most enjoyable experience. So once you start to realize through the modeling what sort of category or archetype the player fits into, you can start bringing attention to the quests, to the actions that the player can perform that fit within that category. So it's based all on frequency. When you start to notice the player like prefers to resolve issues with fighting, then you start rewarding that and allowing them to build skill in that area, get weapons and other opportunities to continue along that path. But if the player is choosing to avoid fighting, then you might de-emphasize fighting as a way forward in the game, maybe present new opportunities. You could say even open up or generate new content according to discovering the player fitting into this sort of a model. And so this can there's other types of models you could come up with. It's going to depend a bit on the game genre. And there's certainly other approaches you could take other than this, which again was originally employed for the tabletop RPGs. So having the sort of player type and fitting the player to these types, it can allow designers to understand their player base, and it can broaden the appeal of the game. So you can make sure your game appeals to these different sorts of categories. Disadvantage though, different games and genres will need their own player types design, and that can be a tricky task. It can take a lot of time to come up with these, and you might miss a category if you don't go through the proper steps to really explore what the different types are. And to actually use the model to drive procedural content generation, it requires a lot of extra knowledge and effort in terms of authoring, because again, all these different actions that are available have to be somehow tagged or identified as being associated with the different archetypes. So if you don't have that information there, you can't act upon it. And so that can make it tricky to use the player types for that purpose. So to close things out regarding player modeling, we can consider how we can use a player model from like an end-to-end gameplay experience. So ultimately, the game, there's a loop in terms of this feedback loop involving the player, but we might prime this loop by starting with player preference. So this could be in the form of some sort of questionnaire. So we query the user to find out maybe something about them that will bootstrap the process, and we feed that into our ongoing modeling of the player. And so during the gameplay, we'll be monitoring player performance and anything else that might identify preferences. And then we'll adapt the game. So some elements of procedural content generation, this could be related to items that are generated, enemies that are spawned, perhaps even changing the nature of the terrain. So you might think of, say, a game like Spelunky. We might actually inform the levels we're generating. And then we will measure the effectiveness of those changes in terms of the updated player performance. And so this is done in such a way that we're trying to determine that the player is enjoying the game. So we might be looking for flow, or that we're awarding behaviors that are associated with what appears to be the preferred category or archetype of play. And we can also use that same information to reperform this categorization of the player types through perhaps like the model-free approaches. And so now we'll get updated models of player types, and that could potentially feed in to new ways of measuring performance, and maybe change the way that procedural content is generated. So this was a very light introduction to player modeling. There's certainly a lot more approaches and issues to consider, but it is also something that there's a lot of research interest in and a lot of interest in terms of commercial game development. I've seen discussion of major game companies like Nintendo being interested in say like biometrics, in introducing biometric feedback into their games. So like being able to measure heart rate or galvanic skin response, maybe even like blood pressure or looking at the player's eyes, so you might be able to detect stress from like the dilation of the pupil in the eye. So I think that this will become a more popular, more and more popular to model the player, not just for sort of a static analysis of gameplay, but rather to have this sort of live feedback loop and adapting gameplay, adapting the content through procedural content generation to optimize the gameplay experience. Hi, in this lecture, we're going to take a look at constraint-based puzzle games. So these are going to be games that involve constraint propagation for generating different puzzles, but there's some typically unique requirements beyond our what we saw with the basic constraint propagation for procedural content, just the nature of some desirable features we want to see in our puzzles. So there are several of these variety of games that such as Sudoku, Nurikabe, Akari, and some others. These are really were popularized by Nikolai Games, and they tend to follow this pattern of being games where the player actually is provided with some clues, and so the player has to propagate the constraints themselves. There's a puzzle element to doing so. But a unique feature of this is that the hints provided guarantee that there is a solution and that it is not ambiguous, meaning that there is only exactly only one valid solution, so one valid configuration, not a variety. And so this is sort of unique to these types of games, and therefore the application of the constraint propagation, that this has to be taken into account. There are other games that this can potentially be applied. So, for instance, the implementation of Minesweeper that you've perhaps played before on one of the old Microsoft Windows releases, that did not guarantee that you were provided with enough hints to solve the board. Of course, it was not ambiguous in that case, but you might not have enough hints. But there are certainly possible, or there's implementations of Minesweeper, not by Microsoft, but by others that do follow this sort of rule. And it's a desirable feature in puzzles. Just, it's frustrating to have a puzzle in front of you that's ultimately not solvable or requires a guess, like in the Microsoft Minesweeper. You might inevitably have to guess, and then, of course, the game could end because you guessed poorly. So we've got a set of constraints defined by our, whatever the rules of our game are. And again, a partial board configuration is provided. Those are our hints. And typically, at least in the Nikolai style of game, the puzzle designer guarantees that there is a solution, that there is only a single solution. And sometimes we'll also specify that a board configuration provides the minimum necessary revealed values. But that's not necessary. In fact, you can have a variety of difficulties by having more or less hints. But it does, potentially, if you're aware of the minimum necessary hints, then that can put it like a bounds on the difficulty of that particular configuration. So qualities of what might be considered like good constraint puzzles is that the player, through experience, they'll discover recurring patterns, which can be generalized into applicable strategies for future puzzles. And these strategies also tend to just kind of fit well with human reasoning, like that, just the ability to visualize a pattern or a problem, and apply it. It tends to follow like spatial reasoning strengths of a human player, as opposed to maybe something that a computer, for instance, would be good at. So there's a bit of an art of selecting the right sorts of constraints. Another feature is the puzzle space should offer a substantial number of unique boards. And hopefully this would be so many that like no one could play through all the configurations in a lifetime. So, and this is also like desirable from these often appear, like in the case of Nikolai, these appear in puzzle books that you can buy at the newsstand or apps. And they make money off of this, so it's nice if there's so many possibilities that it keeps people busy as long as they're willing to play and pay for the new content. And you don't want to have a situation where like you have to like make a board that's big enough to have enough possibilities, but also gets too difficult. So there's kind of like a sweet spot of overlap where the board size provides enough possibilities and the constraints limit things in such a way that it's like human solvable. And then the last feature, I would say, puzzles range substantially in difficulty, supporting a broad range of skill levels. So you want to have, in terms of another ideal feature, you want to be able to introduce some simple puzzles that are easy to solve. These are great for training opportunities, just teaching the rules of the game. And then players can progress and then take on more and more challenging puzzles. And so probably the best known of all of these is Sudoku. Certainly it's a fun one. I personally like Nurikabe, which is also a Nikolai game. Just fits a little bit better with my sort of reasoning, but Sudoku is a great one. Also, it's great for sort of explaining the whole concept of these constraint-based puzzles. So in this case, that we have this 9x9 board, and all the cells in a completed board would contain numbers. And in particular, each row, column, and region has numbers 1 through 9 with no repeats and no numbers missing. So, for instance, every row and column, you're going to be able to find 1 through 9. And then maybe a little bit more tricky part are what are these regions, which are these 3x3 groupings. And you can see the more bolded sort of line on the figure shown here where those groupings are. It's also the third of these 3 figures to see where what is considered a region. So, so that is all that is defined for the constraints, and you typically will be presented a puzzle is presented to you, the player, as having just some handful of hints. So some of the numbers are provided to you, and that's your starting point. And then you can start considering the constraints that you're aware of, which are the unique numbering 1 through 9 on every row, column, and region. So let's consider this problem from like Nikolai's perspective. How do they generate a board? Well, I don't know exactly what their process is, but it almost certainly involves some sort of programmatic support. But let's consider a very naive sort of approach. We might randomly generate a number from 1 to 9 for each cell, and then just iterate through the rows and columns 9 by 9, just randomly generate a number and stick it in there. So what could go wrong with that? And so we're very likely to have mistakes. We're going to not have the correct constraints. We're not performing the sort of collapse and propagation that we discussed before, with the general case of constraint propagation. So clearly, just that sort of naive approach of trying to randomly generate. If we did that, we might be waiting forever until we can finally find one that's valid. So a better option would be to perform the general sort of approach of constraint satisfaction. We're going to randomly select numbers, but for each selection, we're going to take into account the constraint satisfaction according to our 3 general rules of unique number in rows, columns, and groups. And so we're going to scratch off past these possibilities. So each cell we might maintain a list of possibilities 1 through 9 initially. As we collapse, those values become, of course, that particular cell where we collapse, that's going to become concrete. That being the only possibility. And then the neighbors related to these rows, columns, and groups, we're going to propagate. Now, these propagations can sort of chain together arbitrarily deep. So you really have to consider all of the as you're generating these possibilities, you have to consider the rows, columns, and groups that are intersecting. So you keep track of what potentially valid solutions are possible in each cell, and only randomly select from those in future iterations. So you're only ever considering what is in this potentially valid set of values. And so you can do this to completion, where at that point you'll have a filled board. And so it should be a legal Sudoku solution at that point. But you don't have a puzzle yet, because now the whole thing is solved. So the next step is, well, we have a valid board, so now we got to make a puzzle out of it. But before we consider how to make a completed board into a puzzle, another option, at least that's possible in the case of Sudoku, is we could generate what would be called a canonical Sudoku board and then shuffle. So this would just be the most straightforward valid board. It's essentially always the same starting point, just through the most straightforward, 1 through 9 on the first row, and then appropriate generations from there. You can just sort of slide, consider each row kind of like a rolling buffer or circular buffer, and then just shift it one over, and so you can generate a board that is valid pretty easily that way. And so that can be like your canonical board. And then so you can perform, once you have that, you could perform some number of shuffling operations where the shuffle operation is provable to maintain the constraints. And so there are these sorts of constraint games where you can define valid shuffling operations, where it's provable that the application of the shuffle maintains all the constraints. So that's like an alternative approach that one might take. If it wasn't provable that your shuffle operation worked, maybe it's has some percentage chance of working, then you might need to also integrate in some sort of validation check. So that's maybe a slight variant that could be applied, or maybe more suitable to some other constraint games, not Sudoku, but some other type, where you might not be able to have a provable rule, but you might have one that's got a high probability that it would be valid, but you just got to do the validation check every time. All right, so In any case, probably most likely we do the constraint propagation with the collapse and propagation. But once we have our complete board, we now need to start removing numbers until there's enough unknowns for it to be an interesting but still a solvable puzzle. And part of being solvable, it means that it cannot be ambiguous as well. So we need to check for that. One approach that we could take is like a greedy algorithm, where we just remove a random number and then analyze the new board state to see if it's still unambiguously solvable. And then we just keep removing numbers and keep doing this check until we find an ambiguity, and then that is our stopping point. And then a slight variant of this is we could take an optimistic approach where we consider that once we reach the point of finding an ambiguous board state from an attempt to remove a number, well, we'll undo the last operation and then iterate through the remaining options in hopes of finding a number that can be removed. And so we'll go through this process, and then if we happen to find another, then we'll reset this and then start again with attempting to remove numbers, and then at that point we finally decide, well, we've removed as many as we can. This might leave you wondering, like, if there is at least for the case of Sudoku, is there a minimum board? So potentially this minimum board would be maybe the ideal form of the puzzle. So the fewest hints would be maybe the most challenging form of the puzzle, or the least solved. But so that would be quite, at least in terms of brute force, exhaustively searching, that would be infeasible to just based on the large number of possibilities that would have to be considered. And so this has been certainly explored as like an interesting problem in mathematics. It is considering these Sudoku boards. And so there's a paper referenced here where some researchers went to quite a lot of effort to try to determine if, from the empirical observation of Sudokus, that there had been, like, I guess, a handful of 17 number clues. So 17 of the total cells on the Sudoku board being provided as a starting point for a puzzle. And so there is some speculation that, well, maybe there is a 16 clue board out there somewhere. And so they went through a process with some pretty complicated ways of pruning away possibilities to identify. So at least the results of their work does give us a bounds of of all possible combinations of boards, that there is not a 16 clue board. So 17 would be the smallest you could ever get. But in terms of the impact on the puzzle, from the player's perspective, it doesn't really matter. I mean, again, you might be able to find a harder version of that puzzle, but there's still so many puzzles out there that it's not really necessary to find the absolute lowest. And it's probably true of many of these types of games, that there's really no specific need to find the least configured starting point for one of these boards. Once you've come up with a means of removing values and getting to a starting point, you're going to have a board that's going to not be ambiguous, and it satisfies the constraints, and you can hand it off to the player, and then the player can attempt to solve the board, and it's straightforward to know whether they've got the solution or not. It's just a question of evaluating according to the constraints related to the rows, columns, and regions. So yeah, we could just stop there and say, okay, we're done. But it would be nice to estimate the puzzle difficulty. So think about the perspective from Nikolai. They want to make these books and have some puzzles to appeal to different types of gamers. And it'd be nice if they could tell the beginning gamers, hey, this is a beginning puzzle, or this is intermediate or hard, or so on. So how do we go about doing that? So one straightforward option, we could just have a human solve it, maybe like an expert, and we just train this expert so like they can solve any of them, but they assign a difficulty. So like if they just breeze through it, that would maybe be the easiest, and then work their way up from there. But it would be nice if we could just totally automate this as well. And so we could consider writing like a recursive solver. In fact, this is really easy to do. Like I imagine anyone taking this class could implement a recursive solver for a Sudoku. But that doesn't tell us anything about how difficult a human will find the puzzle to be. So how might we do this? And well, one, it certainly would complicate our implementation, but it'd be nice if maybe we could implement human strategies. So pretty much everyone arrives on the same set of strategies, especially for the most basic steps. It might give them different names, but in fact, if you read like any books or websites about Sudokus, and maybe after you've played several, you'll be like, oh, well, they've got a name for this thing I've already been doing. And so, a lot of these strategies you come up with, you generalize a propagation of constraints. It's very shallow. So these sort of shallow propagations, and they tend to have these like visual patterns to them, something that you can quickly kind of pattern identify kind of. And so here's a list of them with the sort of common names that you'll find, like only choice rule, and these kind of go from the simplest to the most complicated. Single possibility rule, only square rule, 2 out of 3 rule, and so on. So there's several of these. And if you play these enough, you'll probably discover all of these or almost all. And then maybe you could even read about and learn the remaining of these popular human strategies. And so you could write a solver that could recognize these patterns. And this is a good bit more difficult than just a straight recursive approach, but it's certainly doable. I would say by your typical undergrad computer science student could implement this. Implement a human solver, exhaustively try the easiest strategy on all cells. And then once you determine there's no ability to apply that, then you go to the next most difficult, and so on. Every time you solve a cell, that you want to reset back to using the easiest strategy again. This tends to follow the human sort of approach. Like you keep screening for the simplest way of propagating the constraints, and then you consider the more complicated ones. The whole while you're doing this, you want to do some bookkeeping and track, which ones of these are using. But eventually, if you do this, you will run out of human strategies. You'll have tried them, and so what do you do at that point? So this is a situation where you exhaust all the human sort of easily identified strategies. So now you start performing recursive guessing. And you could just go from there. But if you really want to do this for the purpose of difficulty, you don't just want to search for just whatever the first possibility is. You really want to do like a breadth first search of searching for the shortest guess that leads to something that you can validate through the rules propagation, that you haven't created something that's invalid in terms of the propagation. So it's basically you find the shortest recursive chain that is either going to definitely solve a cell correctly or exclude a possible candidate number from the potentially valid set list. And so once you've have a valid change to the state of the board, then you fall back to the human strategies again and try all those. It's quite often that once you do the sort of brute force with a recursive approach, then suddenly the easy strategies open up again as working. So yeah, you record a tally of all the strategies used, and then if you have to use the brute force approach, then you might tally that as such, but also what's the chain length that you had to go through to validate it. And so then from all that, you have a heuristic that you based on this tally, you come up with like some kind of scoring. So maybe if you're using all the simplest strategies and nothing else, that would be a 1. But let's say you had all simple human strategies and there was like one hard step, but that was it. Then you might jump from 1 to 3 stars out of 5 maybe. But if you have a number of these more difficult things, then that might boost you. So you come up with some reasonable heuristic for that, and it might not really be a perfect reflection of difficulty, but at least this allows you to automate. Another strategy I'm aware of is from this paper, The Chaos Within Sudoku. And so these authors, they used a continuous K-SAT solver. So it's a continuous time dynamical solver. And they came up with a measure of difficulty based on the length of time that their solver took to come up with a solution. And it tends to map pretty well to how a human might score the difficulty. And so this is fairly complicated implementation, though it's interesting in that just even looking at the graphs of how their solver iterates through different collapsing, selecting, collapsing different values and how those propagate through their solver. So for very simple boards, you can see that the structure of these graphs, basically the little graphs are reflecting like the selection and like the collapse and propagation of different values. And so you can see that a simple board, there's maybe just 1 or 2 guesses. But a hard board, you can see there's a lot of noise in those. And that's really a reflection of just lots of combinations that are being evaluated. And they also had some other visualizations that were showing the parameters that come into play in terms of going through all the different possibilities. And so these easy boards tend to have these very simple structures to visualizing these parameters, but the hard ones tends to present these almost fractal-like patterns. And then this last picture here, this shows graphs for different boards that were, or the lines show different boards that were solved. And so I believe when you start off with the at the top of the value 1, that's the board is not yet solved, and then you sort of work your way towards 0. And at the point that 0 is reached, just the nature of the way their algorithm works. So after some period of time, when you hit 0, that means you've resolved and have the solution. And so very easy boards, you see, are solved very quickly in their time units. And then we see a handful of boards easy to solve, and then progressively harder and harder boards. And so they were really interested in finding the most difficult to solve boards, and so you can see that there's some that almost appear to well, that they go off the edge of the graph, that you never actually see them curve down to the point where we hit the actual completed time value. So in fact, they zoom in on that section to show those hardest boards, and trying to identify what would be considered the very hardest board. And of course, you can read the paper and actually see the board and try to solve it yourself if you're interested. But yeah, some of these just have like the perfect combination of values, or the configuration. The values are such that it's just incredibly hard, with extremely long chains that you have to consider before you can finally say that, okay, this is a particular value, for instance. So this actually is a very interesting approach, and it does a good job. It kind of has like a nice uniform spread. So in terms of signing these difficulties, it doesn't necessarily capture what are the propagations of constraints that are easier for a human, because some of the some of the chains that like visually you can recognize yourself, just these kind of rules that you internalize, they might, involve some bit of depth, I guess, to in terms of the constraints that like the chains of constraints considered, but they jump out at you, and that those won't necessarily be captured completely by something like this. But overall, I think this is interesting, and it really does a good job of separating out the very, very hardest from just the pretty darn hard sort of problems. So hopefully you found this interesting, just taking a little bit of a deeper dive into the constraint satisfaction sort of procedural content generation, because these sorts of constraint problems, they do have some kind of unique challenges in terms of generating the content, just because the constraints themselves are involved in the challenge for the player. They're not hidden away. These aren't hidden implementation details like generating a 2D level or terrain or something like that. They're actually part of the game. And then we also have that interesting bit with the not wanting the ambiguous solutions, because that makes these sorts of problems difficult for a human to solve, and ensure that they're haven't made any mistakes and that sort of thing as they work their way through the problem.